Hello again, folks. Today I'm going to be covering the solutions to the file that I had sent you, which looks like this. Basically, this is a copy of it that's available to you. There are 36 individual problems on this, and the first 15, I'm sorry. As I mentioned in the email I sent you, the first 15 I took from the original test that you had, and I think it was like the end of February. The problems that follow it are the things that you hadn't been tested on yet. Alright, so I'm going to go through the whole thing, but just so you realize, if you want to skip ahead in the video for whatever reason, alright, 16 is the newer material, starting from 16. Okay. Alright, let's see. Alright, now, problem 1, let's see if this writes. That's pretty good. Okay. Problem 1 is a question of using the distance formula. You're given these 2 points, -8, -8 for your x and y value, first point, and -1 and -9 for the second x and y. Alright, and the only thing that you really have to do is dig up the distance formula, which I'm going to write in green because it's kind of faint anyway. The distance formula, hopefully it's legible, is the square root of 2 x's subtracted and then squared, plus the difference of 2 y's subtracted and then squared. And it's up to you to decide, alright, well, which is the set of x1 and y1? My logic is that if this shows up in your face first, then just maybe make little labels to designate these, the set of 1s, and this, therefore, the set of 2s. Can you do it the other way around? Certainly, right, if you want to. Just be consistent. In other words, don't blend together, you know, an x1 here and a y1 there. Okay? So if this is the way, it doesn't matter which way if you made these the 2s and these the 1s. If you put them in, eventually you'll get the same exact answer as I am doing it. So just be careful with signs. -1 would be situated here. There's a negative in the formula, and then this is -8. So in this instance, you would have to double it. A double negative is a positive, right? And then one of each would dictate that you actually subtract. So in this case, you have +7 squared, and then this is 49. Now over here, you would have just coincidentally the same digit of 8. But I'll do 9 first, minus an 8, and then again a double negative, so this ends up being 9 plus 8, which is 17, and 17 squared is 289, good. 17 times 17. Okay. Then, following the order of operations, you would add this, and you would end up with 338. Now bear in mind this is underneath the radical, and even though you might guess, well, that is technically an exponent of 1/2, why didn't I do that first? Because you can't take the radical of individual terms, right? You have to combine them first. And that's this is one of those situations where you're sort of bending the rules, right, I suppose. Anyhow, the square root of 338 gives you something like 18.384. I think I wrote on here, round to the nearest hundredth. So this 8 sitting in the hundredths place, based upon 4, you would round this to approximately 18.38. Okay, units. And that would represent the distance between 2 points. So I'm just guessing here. If you figure that's something that has a negative and a negative for the x and y, it would be in the 3rd quadrant. And if you had a negative x and a positive y, it would be in the 2nd quadrant. So you'd have a line that you've calculated the distance from that would be diagonal, like this. This is not to scale, but that's basically what it represents. So this would be a distance of approximately 18.38 units. Now, as you'll see in the next couple of problems, if this was part of a circle, if this was in fact the diameter, the endpoints of the circle, you could use this to also, cut it in half and get the length of the radius. Alright, let me erase this. Oh boy. Blue is going to be a nuisance today. Okay. That means that particular blue marker is going away. The problem is I put it into a bucket of 5 or 6 blue markers. So now I have to test them as I'm using them. I hate that. Some of them are defective. They're behaving as though they were permanent markers and they're not. They're supposed to be dry erase. So I believe it was this one. So I can't throw this anyway, but put this up in the corner here so I don't use it again. Okay. Pardon me. Problem 2 is a question of midpoint. So in the case of 2, you're given these coordinates, which are -19, 9, and the second coordinate is the second wooded pair is 11, 13. Okay. Again, you will have your, in this case, midpoint, which is the location of halfway along that a similar line. Sometimes midpoint is abbreviated MP. In this case, it is the sum of 2 x's and the sum of 2 y's divided by 2 each. Okay, so again, take a little artistic license. Decide for yourself which is the set of x1 and y1. And to me, again, I do it this way. This shows up first, that's the 1s. This shows up second, that's the 2s. Okay. Let's see. -11, and there's a plus in the formula, and then there's a 11, and 9 and 13. Okay, hopefully that's not too faint. Combine these two, one of each sign dictates that you actually subtract, in which case you get -8. -8 divided by 2 leaves you with -4. 9 plus 13 is 22, and 22 divided by 2 is 11. This is the location of halfway between these points. And again, just to give you a rough idea what this is after, you can imagine a coordinate plane, and this is a -x and a positive y, which means it's probably in quadrant 2. And this is a positive x and a positive y, which means that it would be in quadrant 1. So roughly something like this. You'd have a diagonal line, and we calculated the midpoint. So the midpoint would be, this is not to scale, but somewhere halfway in between these two lines, these two dots. -4, +11. Okay. And then essentially the last of this type is to go the whole 9 yards and to write an equation of a circle. And you might find that you incorporate both of these formulas, the distance formula and also the midpoint. Okay. Okay, now a couple of things to remind you. Look something up because I want to show you. may remember from a while back I had drawn you a diagram like this, and if not, let me replicate it. We've been using formulas, which are useful equations. Right. And famously, there is the Pythagorean theorem. A squared plus b squared equals c squared. Right. This is specifically for right triangles. And although these two dimensions, a and b, are interchangeable, the one thing that is non-negotiable is the c dimension, which is the hypotenuse, which is always across from the 90-degree angle. And it's from this that basically the distance formula is derived. The labels have been changed. So instead of calling this hypotenuse c, we call it d for distance. And instead of leaving it as squared, we take a square root. Then to get the dimensions, which would be the side lengths of a triangle, we have to subtract x coordinates and y coordinates. Squared, squared. Okay. You would see that if you ended up with something that wasn't a diagonal line, that the intricate calculations would, simplify. You may not end up with an x dimension at all, right? Pardon me, or y dimension. It would subtract and cancel. From this, we get the equation of a circle. And it officially is, again, changing the dimensions. So if you see something like, instead of calling it d, we call it r, as in radius. And I'll leave it squared in this case. The dimensions that are the two x's, one of them would be changed to call it h, and the other would be changed to call it k. Let's see if this is visible. Looks like it's okay. Sorry for the scar here, but hopefully that's not interfering with you seeing this. Okay, this is the formula for the equation of a circle. It's just backwards, all right? And you might wonder naturally, well, why call these h and k instead of a second x and a second y? These are the coordinates of the center of the circle. So giving them another letter essentially is to designate special purpose to them. Makes them seem more important because they are. All right. Okay. Now, in the case of problem 3, let me just encapsulate this. Okay. As a side note, we have our midpoint formula. Let's see if it will have to help. It's always debatable. If it gets too hard to see, I'll turn on the light again. I'm digressing. If these are the coordinates that you are given, 2, 12, no, let me just pick up the paper, that would be smart. 2, 2, and 12, 2. Right. What I would do is, since I'm tasked with writing the standard form, of the equation of a circle, which again would look like this, rather than with the square root. These coordinates, which would be in the first dimension, in the first quadrant, both of them, because they're both positives. X's and Y's are both positive in each case. This is probably not necessary, but let me just to emphasize, I'll put this like this. If you were to plot these coordinates, and it might illustrate the point a little better if I take the time. Positive 2 would be an increment here, and up 2 would be an increment here. So you'd have your first dot here. If I went out 12 spaces, that would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then up 2 as well. And what you would end up with is a perfectly horizontal line, rather than the usual thing, which is a diagonal line, right? Even in a triangle, a right triangle, usually the hypotenuse is representative of a diagonal line. Right? Anyhow, when you plug in the ordered pairs x1, y1, x2, and y2, you'll see that the calculation accounts for this being horizontal. All right. There's a couple of things that we have to identify if we want to write the equation of a circle. We need to know what the radius is, right? And the radius would be, if you figure this is part of some imaginary circle here, it would be half of the distance. So I'm going to start with the distance formula and then divide it in half, all right, to get a radius, all right? So what I'll do is I'll insert 2 and 2 and 12 and 2, all right? If this is x1 and this is y1, and this is x2 and y2, then this would be 12 minus 2, and in the case of the y's, 2 minus 2. And already you'll see what happens with the arithmetic involved here. I really should do this first. 12 minus 2 is 10, and then 10 squared would be 100. When I go to straighten out the second portion of this, 2 minus 2 ends up being 0. 0 squared is just 0. This term cancels out of existence. And the reason being, because the y dimensions are the same, you have a horizontal line. Anyhow, we'll take the square root of this, all right, which is 10. And then as an afterthought, because we're looking for a radius again, instead of this being a distance that is a diameter, I need half of that, which is a radius. See if that's visible. Looks like it is. So half of 10 is just 5. Okay. In this portion of the formula, a 5 would be appropriately placed. Okay. Now as for the center of the circle, if you do this on graph paper, you wouldn't need to do a formula, right, or to use a formula. What you could do is just read the coordinates, right? Being that it's a horizontal line, it's not an unfair assumption to count, okay, how wide is this? We've just decided that from here to here is 10, right? So what's half of 10? 5. If you count 5 increments in, 1, 2, 3, 4, 5, this would represent the center of this, and then you could just read it on the coordinate graph, right, using the grid lines. I'm going to assume that a person doesn't have graph papers. So I'm just going to do the calculation for the midpoint, because the midpoint would be the location of the center. So again, I'm going to input x1, y1, x2, and y2. And in this case, it's going to be 2 plus 12, and then 2 plus 2. Yep. And do the arithmetic. All right, 2 plus 12 is 14. 14 divided by 2 is 7. And 2 plus 2 is 4. And 4 divided by 2 is 2. The location of the center is 7, 2. All right, let's just verify. 1, 2, 3, 4, 5, 6, 7. And then up 2 spaces is yes. All right, exactly where the graph, if drawn, would have predicted. So that means I'm going to say, all right, I'm going to have to insert this into my standard form of the equation of a circle in place of the h and the k. All right. Notice that we got positives for this location, rightfully so. In the formula, there are minuses. So if you were going to start from scratch, if you had the formula given to you, just realize that it's counterintuitive. It means if you were going to draw this from scratch rather than craft this from scratch, just realize that if you see a -7, it really is indicating that the center is at +7. And if you see a -2, as you would in the case of this y value, that is really indicating that this is a +2. Now there is one other thing I could do, which is to clean up my little mess here, because it is sloppy. And maybe put the radius value in front. And I'll do the actual arithmetic. So if it is 5 squared, call this 25, is equal to the difference of x minus 7 squared plus the difference of y minus 2 squared. And this would be the equation that describes this imaginary theoretical circle here. Which would be, one of the choices, choice E. All right. Next one is an exercise in finding the x and y intercepts for the graph of a quadratic equation. So in this case, let me just write it here. Rather than torture myself, I should probably just hold on to my paper. This is what's given to you, this equation. Y equals x squared minus 8x plus 12. And you were asked to find the x-intercepts and a y-intercept. That's usually the case. You usually have one of these and two of these. Doesn't always happen, I suppose, but it will in this instance. I do wish my glasses would stop slipping off my face. Let me get rid of that. Okay. This blue is a wee bit better than the last one. So I'll keep that. I have to identify which other ones are trouble. Put this aside. Okay. You don't need a formula, you need a procedure if you're going to have to identify x-intercepts and y-intercepts. It's a little counterintuitive, because when you think of the x-intercept naturally, you assume, oh, okay, I'm messing around with the x's somehow. Not so. What you're going to do to find this is you're going to place a 0 into y. And when you're going to find the y-intercept, you're going to do the same thing almost. You're going to put a 0 in place of x. So you're using 0 twice. Let me write this formula in two places. And hopefully it will show it visibly. Green is always a trouble. Now, if you follow this procedure, if looking for an x-intercept, you stick a 0 in y, that means that there will be a 0 here. All right. Essentially, what's going to happen in this case is that you're going to attempt to factor this half of the equation, and then use or incorporate the employ the zero product rule, which is a way of figuring what the x values would equal once factored, which means you're going to put things in parentheses. Now, being that this is a relatively simple trinomial of x squared, usually what happens when you have a trinomial that is degree 2, and I'm calling this a trinomial, of course, because it has 3 terms, and there's no lead coefficient here other than 1, you could pretty much tinker with this and go directly to how it factors, which is usually a binomial sitting next to a binomial. A good habit would be not to jump the gun as I am, all right, and attempt to factor out a GCF. It just so happens that in this case the GCF is 1, so we're going with the more complicated method here. Anyhow, if this is x squared, you could probably bet that this is going to be xx here and here. As for 12, you'd have to consider all the pairs of factors as different combinations that make 12. 1 and 12, 2 and 6, and 3 and 4. Thankfully, it's relatively small amount. But of these choices, all right, 1 and 12, 2 and 6, and 3 and 4, what is probably going to make the middle term 8? The only pair that would work would be 6 and 2. Now, as an afterthought, I would deal with the signs. And you always talk yourself through it like this. These are going from something smaller to something larger. If in theory there are two choices, adding and subtracting, which one of those causes things to get bigger? Adding. If you want them to add, they have to be the same signs. Same signs essentially causes adding to occur. But which same signs? Both positive or both negative? If the negative is the end result here, then these are going to be both negative. And just to double check, a negative plus a negative is a bigger negative. Simultaneously, a negative times a negative is a positive. It's all hunky-dory. Everything is shipshape. Okay. So, I don't know, I'm getting a little breathy. At this point, we have it factored. This is a factor, this is a factor, they're being multiplied, and it's also set equal to 0. So we can employ the zero product rule, which is suggesting that perhaps this chunk unto itself is equal to 0 in order for the whole thing to be true, or perhaps this chunk is equal to 0, or both of them. And in which case you end up with two smaller equations to have to solve. All right, not too bad. In this case, you would add 2 to justify moving this, and x would be at the location of positive 2. And in this case, you would add 6 to justify moving this, and x would be positive 6. Now to remember, these are x-intercepts, which are ordered pairs, coordinates. So in this instance, it would be 2, comma, what do you use for y? 0. And in this instance, this would be 6, comma, 0. This is dying. Oh boy. Thankfully I bought a new package. We'll see how long this goes. Alright, so these are all x-intercepts, 2, comma, 0 and 6, comma, 0. This one is super easy by comparison. There's no factoring involved because it involves using a 0 in place of the x's. So there's no 2 here, sorry. If you put a 0 inserted into here, I always draw these little parentheses as like a little pocket that you're going to fill, just in case there's a sign. In the case of 0, there wouldn't be, but 0 squared cancels out of existence. 8 times 0 cancels out of existence, and basically what that means is that you have 12 left over. And in the style of a coordinate, you would have 12 for the y value, always written second, and 0 because that's what you use for this calculation. So this is your y-intercept, and these are your 2 x-intercepts, which if you wanted to, you could draw, you could plot those coordinates already. You have a pretty good fleshed out parabola. Okay. Anyhow, this would be choice E amongst the choices. Okay, in the case of problem 5, it's multiple choices and you have a graph to match. You have the equation given to you. Is 5. Let's see. Y equals 4x to the third plus 4. All right, a couple of things. We have a model that we have established at this point, which is of transformations. Where did I put my marker? Okay. Let me write it here. Y is equal to plus or minus a times x minus h. I'll put an n here for the degree, plus k. Okay, and each one of these letters has some job in order to transform the parent function. All right. The parent function is decided by the degree here. So if you have right already an x to the third, what graph type does this most closely resemble? It would look like this. All right, remember from amongst your parent functions, when you have sort of a parabola that is, I hate to use the term, but it has a stroke on one side. It's terrible, right? It's a parabola, or you might say this is a little bit more of a genteel. It's doing a dance. It's doing the staying alive, right? a parabola would be, I'll just draw a dash like this, something that is blooming up like a tulip. All right? But instead, in the case of x3, you would get a graph that looks like this, all right? And these points would be relevant, right? We'd go through the center, the origin, and at least in the non-transformed incarnation of this, just the parent function, it would go through the points 1, 1, and -1, -1, like so. Being that this has a 3 in it, we would expect that it's going to have a similar picture to that, right? Then there's all these other features here, some of which are included in the example and some of which are not. If you had a negative up in front, then that would basically flip it upside down. You would say that it would be vertically reflected, or, you know, flipped. We have a positive, so it's going to be oriented exactly like this. Then, if there were a parentheses, and there isn't in this case, you'd have a horizontal shift, which again is counterintuitive, meaning that if you saw a negative, it would actually imply moving in the positive direction. Right. And then there's this dimension here, which is a vertical shift, which is thankfully intuitive, meaning what you see is what you get. So if you see a positive, it means moves up. That is the only thing aside from this dimension here, which is a vertical stretch. If you have a whole number, what that usually means is that it's elongated your picture. It's transformed in that sense that it is stretched vertically. So what would happen is that it wouldn't go through 1, 1 here, or -1, -1 here. It'd be a little bit more exaggerated like that, a little bit more steep and narrow. All right. Anyhow, let's consider this, since that's the easiest to tinker with. You have a k value, therefore you have a vertical shift. If you took all these points and then added 4 to them, that'd be where your graph would be. So there's my faint color. If you added 4 to the origin, right? Instead of being at 0, 0, it'd be 1, 2, 3, 4. You'd have a dot here at 0, 4, right? If I didn't have this extra vertical stretch and I added 4 to this, then this would go up to 5. So at the location of 1, and it goes from -1, from +1, 1, add 4, you'd go up to 5. 2, 3, 4, 5. Similarly, if you added 4 to -1, you'd go up 4 from -1. So if -1 is here, 0, 1, 2, 3. Okay. And you'd have a dot like this. This is basically what the picture would look like. It would be a little different, only for the fact that there is this vertical stretch factor of 4, which would make this a little bit more exaggerated in both of these cases. Anyhow, the choice that this most closely resembles would be something like D, right, of the choices. It would be a little bit more narrow vertically. Right. If you want to remember, I know that for our college, we are not really supposed to be using calculators, but after a while it starts to get silly. So what you could do is, if you have a Texas Instrument calculator or the emulator, type this in, right, and you'll see what the effects are. They make you go through the trouble anywhere else to learn how to transform a parent function because it's practical, right? It makes you, if you understand what the purpose of each of these terms and factors would be, that they have a job essentially, you could make an educated guess about what the picture would be. And then you have your calculator to verify. So in this case, I'm just going to type this and show you that it gives you the same picture. Y equals 4x to the third plus 4. And hit graph. My calculator has to be adjusted, so I'm going to hit zoom. And then go down the list here. Zoom fit, let's see how that works. Sometimes it does. It's a little bit better. Nah, it's lousy. 6. Standard, thank you very much. There you go. If I hit trace, you see 0, 4 is what is maybe arguably the most important point, right? The center of this. All right, if you wanted to figure out what it would be at the location of 1, right? Since it's probably not going to be 4, it'd be a little bit higher. All right, you can now at this point press 1 for the x value, and then it will spit out what the y should be. It's 8 apparently. Okay, so it's a bit higher. Right? It's more stretched, right, than without that factor. Okay. Number 6. All right. Evaluate the function at s plus 2. All right. Normally when you see it, this is getting bad, huh? All right, another one back to the test. Okay, that's a little bit better, right? When you normally see function notation, especially to start, it's an italicized F in parentheses and then an X inserted on the inside, right? Essentially, the reason for this style of writing an equation is to emphasize what the input is. Meaning this is the variable that you're messing around with, right, when you're evaluating. In the case of problem 6, they opt for using a G instead. But what they're telling you in this case is that you want to evaluate the function using not what would be satisfying, which would be just a regular ordinary number like 2, but an algebraic expression, right? To see how well you grasp the concept of basically inserting and then simplifying. So instead of seeing something like this, 12 minus 5x, right? What you see in this case is 12 minus 5y, right? Because what normally is here, well, in this unique problem is that they're saying that it's y, okay? So here's your function that you have in this individual problem. They just opted for calling the input y instead of x's. And then they're saying, all right, insert this instead. In other words, wherever you see a y, which would be over here, you're going to put s plus 2. So it will be 12 plus 5, and then you're going to go about your business here. So if I'm going to stick s plus 2 in the function, then I'll put it here. And then evaluating, right, using that algebraic expression. So this is an exercise in how well you can simplify following the order of operations. Why the order of operations? Because when you're trying to simplify, you're just exclusively paying attention to one side of equals, not both of them. Function notation is on the opposite side. That's more or less the instruction. So you're just going to distribute 5 here. You get 12 plus 5s. It's a little bit too stylized. Plus 10. And then combine what you can, the like terms. Regular ordinary 12 here and 10 can be combined. So this would be 5s plus 22. And this is how you might write it to be fancy. All right. The function evaluated at s plus 2, whatever that is 5s plus 22. Oh wait, I changed the problem. All right, sorry. If this was positive, that would be swell, but the actual problem was negative. I just didn't transfer that when I should have. Okay. So this would be 5s as it is negative 5s. And then negative 5 distributed to positive 2 would be negative 10, right? Which means that this would be regular 12 combined with negative 10, you actually subtract, and you get a positive 2. This is what you would have. Negative 5s, because of that negative there, plus 2. In the choices, they wrote it backwards. So I prefer to put things in descending order, but I guess because there's a negative coefficient here, they felt it looked nicer to write it like that. Okay. Same difference, literally. Okay. 7, it says find the domain of the function. What is the domain of this function, which is a radical x plus 4 sitting on top of 4 plus x. Now, if it was one or the other, it would be bad enough. In this case, let me remind you of something. Oh, that's faint. When it comes to domain, not exclusively, but usually what that means is that this is what x's are allowed. When you think domain, 9 times out of 10 it's referring to the x. It's just that in some other parallel universe, if you wanted to change, with some unique set of circumstances, you could change the y to the input variable, an inverse, right? Then you would call that the domain. Anyhow, it's usually just what x's are allowed. And there's 3 scenarios to look out for. If you have a polynomial, you usually don't have to worry too much. And a polynomial is something that's built out of this building block. It has a real coefficient, it has a non-negative exponent attached to the variable. And it may be several terms or just one term. If you have a radical, as you can see, this is incorporated here. In that instance, you would augment this ever so slightly. I'm going to write literally what is there. See if that's not too faint. Instead of you have a real coefficient, but instead of having a non-negative whole number, an integer if you will, you would literally have a fraction for an exponent. That's an example of having something in rational notation when it's in the style of a fraction. For example, x with a little radical hat on it, if you will, can be instead written in this is radical notation. You would call this x to the 1/2, right? This is rational notation. And then there's this third situation where you have a rational equation. I'm running out of space, so I'm just going to kind of abbreviate here. Similar looking building block, but you have a negative exponent, which is not usually written. This is an example of, let's just say, x to the -2 really represents 1 over x squared, or -1 would be easier. When you have a negative exponent, that is an instruction to write this as a denominator. Okay. When you have a fraction for an exponent, that refers to this as having a radical. In theory, there would be a 2 here and a 1 here. In the case of square roots, they never bother writing those numbers. Right? And if you have just a positive, or usually, it can be a 0 as well, technically, but if you have the normal case of a positive exponent, you don't have to worry so much. In terms of domain, right? Now, what's the domain of a polynomial? Virtually all real numbers, which is abbreviated by that sort of Gatsby-esque 1920s style R. Right? In interval notation, that would be symbolized like this. What are the x's allowed to be? Everything from -infinity to +infinity. In terms of radicals, the conditions are such that the radicand, how do I abbreviate that? I hate to say this. This is the fancy way of writing it. You'd see something like this. In the most basic type of this, the square root, the x value has to be greater than or exactly equal to 0. It could be any other x as long as it's that, all right, satisfying that condition. That is in set builder notation. In interval notation, similar to this, what you would see is it can be equal to 0, so they put a bracket as a lower boundary, and then +infinity, a curve here because it's infinity, it's not a specific place, would be the upper boundary, which is kind of a misnomer because it's not a boundary if it's infinity, right? In this case, for rational functions, if you can conceive of it, let me ask you this question. What is the one number in the world that you're not allowed to have as a denominator? 0. Because it would be undefined. You can divide into 0, you can't divide by 0. In that instance, if you were going to write this in fancy notation, set builder notation, it might look something like this. A little no smoking cross out. X can be anything as long as x is not equal to 0. This line here is such that in interval style of notation, it would be something like this. It would be the most complicated of all of them. So I'll write this in red. There'd be a union of negative up to 0, not including it, curve. Then the union symbol would be in between, and then just because I'm running out of board space, there would be this. It would pick up from 0 and head into +infinity. Basically, there would be a gap in the graph. There's a spectrum of what x is allowed to be up to, it comes to a crashing halt, which is 0, does not include 0, then there's that gap, and then it picks up on the opposite side, all right? Just doesn't include 0, and then it stretches into +infinity. There's a hole, basically, in what the domain of rational functions can be. All right, anyhow, that summarizes. Now, in this particular problem, you have both situations going on. So what you will need to do is ultimately figure out what the domain would be for the top and the bottom. And then consider their intersection, which is, instead of using a union symbol, this symbol, right? Basically, we want to satisfy both conditions, both the top and is what intersections usually refer to as the bottom, the denominator, if you will, must be satisfied simultaneously. Okay, so we're going to draw a lot of pictures, is basically it. Let me get rid of this because it's just getting in the way. And I'll erase some of this up here. Blue is a nuisance, apparently. Put that here. One more. Okay. If you want to get yourself rolling in terms of figuring out radicals, what I would suggest you do is follow this sort of formula. Take whatever the guts of the radical are, known as the radicand, and write a teeny tiny sort of inequality-esque equation. I can't call it an inequation, they don't call it that. It's an inequality. Take the guts, the radicand, what's underneath this little house hat, and write that. And in the case of rationals, you have something similar. Blue. Write a little sort of an equation like this. The denominator not equal to 0. So we're going to end up, which really just means you're going to factor and sort of consider the 0 product rule, but you have to remind yourself at the end, it just doesn't equal that. All right. In this particular problem, we'll start with the top here. If I consider this radicand of x plus 4, it has to be greater than or equal to 0. If I were to solve this, I would end up having to move 4 via subtraction, and x would be something greater than or equal to -4. I'm going to draw a picture to illustrate that. Let me erase some of this because I need the space. The graph that would come from this, and sometimes the picture is better because it's helpful in trying to figure out what the intersection will be. I'm going to use 0 just as a separator between negatives and positives, and then I'm going to plop this -4 on the appropriate side, and then I'm going to talk myself through the process. I'm going to say, well, this has an equals in it, so if I'm going to use the old-fashioned symbols to represent inclusion, I would put a dot here rather than a hole to say, yes, -4 would be allowed in here to start with. And then it would also have to be things that are greater than this. So there would be an arrow stretching off this headed in that direction, the positive infinity direction. If I were to deal with this situation, that's a bad green. I would consider the denominator, and the denominator would be 4 plus x not equal to 0. If it was more complicated, let's say it was quadratic, I would try to factor it. In this case, it doesn't, there's nothing else you could do with it. So I'm just going to manipulate this by moving 4 by subtraction. And this would demand that x not be equal to -4. It can be everything but that. Essentially. Now on a separate graph, which I'll put just underneath here, -4 would be in the same place. I'm going to use 0 always just as a separator. How would I represent, using old-fashioned symbols, non-inclusion? Something is excluded. I wouldn't use a dot, I would use a hole, basically, at that location. Saying that as a gap, right? If it could be everything but that, there would be a line stretching this way into positive infinity and a line stretching this way into negative infinity. Now, what I need to do is, whether in my mind or I draw a third picture, superimpose these two graphs, right, to see that both the top and the bottom are satisfied, right? Basically, what I need to look at is the overlap only. So I need to erase something because I need the space back, but let me move some of this. And I'll put the next drawing just above the blue one here. I'll do it very faintly in green. Here's 0, here's -4, coincidentally the same number. And now I'm going to sort of draw both of these, the blue situation and the red situation, on top of each other. So here's blue, the top. I'd have a line stretching that way. Here's the red situation. It would be a hole in the same location, and there would be a line stretching that way, and then a line stretching this way. If I am concerned with satisfying both conditions simultaneously, then again, I need the overlap only. That means that in terms of these superimposed pictures, this much is no longer relevant. All right? So I'm gonna, basically my focus is just gonna be moving this way to positive infinity, and therefore that's the upper boundary of in my interval. And then I have to consider this hole with this dot. In order to satisfy both conditions simultaneously, I absolutely positively cannot use -4, which means that if I had to choose to go with the dot or the hole, I have to go with the hole. And this would be my graph. A hole at that location. So that's the lower boundary, -4. Now, as far as interval notation is concerned, is it a bracket if there's a hole here, which means it's not included? No, it would be just a curve. It's unfortunate that it looks like a coordinate, a pair of coordinates. It's not, right? It's this is an interval, a spectrum, a dumbed down version of this drawing, all right? Okay, so that would be what the domain is. -4 to positive infinity. Of your choices, if you notice, C is more verbal than it is symbolic. What it says for choice C is all real numbers such that x is greater than 4. If I wanted to put this in fancy notation, that would sort of explain that verbally. all real numbers, all real solutions for x such that, and then you would read the specific conditions. This inequality summarizes this spectrum. All right, if I shaded it here, it would look a little bit nicer perhaps. Okay. X is greater than -4. It's not included. There's a hole there. Okay? That's choice C. Okay. Let me erase this now. I'll wait for time. We're an hour in. Let's see. 8 is really easy. For problem 8, it asks you to decide which is not a function using graphs. Given graphs. That was my aunt. Aunt, you gotta get out of here, man, before you get hurt. Alright. This thing moves a little too much. I don't want to hurt her. Alright. This is my math aunt. Alright. Anyhow, if something is not a function, it fails the vertical line test. The vertical line test is basically just drawing imaginary vertical lines through a graph. Alright? And you would, in order to pass, would be only one intersection per line. That means that if it fails, and in this case you're kind of hoping it would, that means more than one. Per line. And I think this red is exhausted now. Put that there. Okay, now as for the choices that you see, just pay attention to the drawings. You have a circle in one case. You have a cubic in another case. It looks like this. And you have a parabola just down here. And then you have a rational function. Okay, so to test that vertical line test, all right, let me start with the easy one, the parabola. If you put an imaginary vertical line through the graph, it would only have one point of intersection per imaginary line that I draw through the curve. So this would pass, which means it would be a function. We want something that is not a function. All right. This cubic graph, one point of intersection no matter where I draw it. So this would also be a pass, which means it is a function. Even the rational, I know that there's an asymptote here, both vertically and horizontally. And it might seem that, well, maybe if you did the one really, really close to the axis, it's curved though. All right, it's infinitesimally curved. So it's always going to be tangent. It's never going to be secant, all right, at this curve here. So this would pass as well, which means that even this is a function. And lo and behold, the circle. Right? Should have done that to begin with, right? This would fail the vertical line test. All right, therefore not a function. So it's that choice, which would be choice B out of these. Okay. 9. Use the graph of the function to find the domain and the range. Okay, so I'm going to sort of replicate what is drawn here. You see a coordinate axis this way and this way, and this is a little too much. And this is x, this is y, and you have two sort of line segments here. One, two, three, four. You have a drawing like this. And just add some distinction here. You have basically two holes. The x value that would be here in both of these cases is -4. The y value would be 0, and in the case of this x, this would be -1 here. Okay. Now, if you were asked to figure out what the domain is, which again is what x is allowed, and then calculate what the range is, or determine what the range is, reckon, right? We'll put it in integral notation, because that summarizes. All right. If you are approaching this gap from the left, right, you are coming from the negative infinity direction. And I'm just thinking about this purely in the x horizontal perspective here. So if you examine any of the dots that this line is in theory made of, and this would stretch beyond the graph, it is implied, what are x's allowed to be? Everything from negative infinity would be the lower boundary here, up to this gap. And since there's a hole there at the location of x -4, and we're talking about the domain, -4 would be the end point here, the upper boundary technically for this interval, and it would not be included, so a curve. Then suddenly the graph would pick up again, all right, in the infinitely tiny gap that in theory would exist. And it would be in the same location of -4. Stretching to positive infinity. -4 would then become, from this point forward, would be -4 is the lower boundary now, and then the upper boundary would be positive infinity. In either case would you use a bracket, they'd be parentheses, right? And because you're trying to illustrate symbolically rather than graphically that there's a hole here, even if it's infinitely tiny, you would call this the union of these two spectra, right? This is one spectrum of solutions, or what x's are allowed to be, then there's a hole, and then and joining that you would have this spectrum. When you're dealing with the y's, there's kind of a similar thing, it's just that the gap is a little bit bigger. So let's say that you are reading now vertically. If you're coming from down under here, this is from negative infinity. So we're going to have a lower boundary of negative infinity, and then it's going to come to a screeching halt when it hits this hole here. Right? In terms of y, though, what y is that? That's y is equal to -1. So the upper boundary for this spectrum would be -1. Then the gap of continuity, discontinuity technically, is a little bit larger than the space in between -4 and -4, right? Which sounds like it's BS, but it's actually true. It's just infinitely tiny. All right. Anyhow, the graph picks up again. It's like an 8. In the gap in the space between -1 and 0. So it's not including 0 either because it's a hole, not a dot. And then it stretches upward into positive infinity, which is also a curve, right? And in a similar way to the domain, you would use this union symbol to represent all of these things in tandem. So there's a spectrum of what y is allowed between these two boundaries. Then there's a hole, right, a gap, of a moment of discontinuity, and then it suddenly exists again. It exists between 0 and positive infinity. All right. Of your choices, this would be choice B. All right, this would be B. It's a funny B. Okay. Here of this chunk. Okay, find the average rate of change for the function from x1 to x2. All right, here is the function. This is problem 10. The function is x squared plus 18x minus 4. And we're trying to calculate the average rate of change between point M1, which is 1, to the point of M2, x, which is 5. Okay, there's a formula that you would need for this. This is the formula. Putting it in green because I want to sort of write on top of it. And you might remember, this is remarkably similar, there's a little thought cloud, to this. Y2 minus y1 over x2 minus x1. There are some subtle differences. This is similar. Okay. Now, ordinary slope is designated by the letter M, and they don't bother to put tangent, but they could if they wanted to be more precise, specific, I should say. Anyhow, it's a difference of y's over a difference of x's. In the case of function notation, you know that this is a y. All right, it's just in the function style. What this is suggesting is that you're going to evaluate the function rather than have the y given to you. And you're going to evaluate the function twice, using the second x value, and in this instance, the second y, the first x value. That will give you what in theory would be your second y and your first y. All right. The reason that this says sec here is because this represents a secant line. And a secant line in terms of a curve is a parabola. Would be a nice thing to show you. If you had a parabola, you know it's not a straight line, it's a curve, literally. One thing that would happen is that the slope of this would change. The slope from here to here would be different from, say, the slope from here to here. And rather than it be tangent to the curve, right, we're using different x values, right? So there's a distance between them, right, in terms of the x's. Anyhow, it's touching the graph, or touching the curve in two places. These are known as secant lines, rather than tangent lines, which would be just touching in one place. Okay, so we're going to basically take this half of the function, because usually just pay attention to the right side, insert 1 and calculate, and then do it again using 5. Right? I'll start with 5 because that's really what x2 is, and this is really number 1. Right. If I did that now, let me place a 5 in here, and we'll see what we get. 5 squared is 25. 18 times 5 is 490. And this is minus 4. And if I follow the order of operations as I should, that would dictate that I add 25 and 90 first, which is what? 115. And 115 minus 4 is 111. So in place of this first function, I would have 111 to subtract. And I'll put a 5 down here as well in place of x2. That's kind of a nuisance. For the 1 here, this would be 1 squared plus 18 times 1 minus 4. This is 1 plus 18 minus 4. This is really 19 minus 4, which is 15. So I would have 15 in here. Let's see. Oh, my ant is back. Okay, ant, be careful. I don't want him to get hurt. Anyhow, focus. 111 minus 15 is 96. I shouldn't forget that there is a 1 here. And so this is 96 over 4, and if you divide these, you get 24. So the slope of the secant using these coordinates would be 24. So the average rate of change is another way of referring to that, and that would be choice A. Okay. I'm starting to dwell on the question of whether it would be appropriate to call something a tangent or not. Well, I'll leave that for another day. Okay, for 11, section 1.6 and 1.7, all right. Use the graph of the parent function of x squared to write an equation for the transformation model. Okay. You have this graph. For 11, you have a picture that looks like this, and they want you to write an equation. This is an increment of 4, and this would be an increment of 12 here. there's more than one way to do this problem. But we'll try to do this fast. Let's start with the transformation model. I'll just start with y because I like that. Plus or minus a times x minus h n plus k. Right? And review what the various pieces do. Okay. The negative sign would cause a vertical reflection. Which means it would be flipped. The A value here would cause a vertical stretch or compression or shrink. Which essentially makes something narrower or flatter. There could be a coefficient here, it's not really going to happen, but if you did, you would have a horizontal stretch. If you have this value here, this is a horizontal shift, which is counterintuitive. And then this is a vertical shift. Okay, and the last thing is, I'm just going to say this space, and then here's my nuisance blue. Okay, go over here now. This, for all intents and purposes, this degree is going to designate the parent. Okay, so given that we are aware of different parent functions, there's a, if nothing else, there's a table that I gave a couple of times. I'm going to draw very simply some parent functions for reference. If you have something that looks like this is an x squared parabola shape. If you have something that looks like this, you have a cubic, x cubed. If you had something like this, that's a nice one. The V shape. This is the absolute value of x, and so forth and so on. I'm kind of beating a dead horse, but if you had a line, this would be x to the 1, linear. Of these four choices, and there are naturally more than these, I'm choking. Which does this graph most closely resemble, even if it is upside down? I would say that this is a parabola. So already I would fill in a 2 in this spot. All right. Another kind of giveaway is, well, it's normally oriented like this. So it's upside down, which means that there would have to be a negative. Right? Anyhow, to calculate A and B, the horizontal and vertical stretches, right, we would need to incorporate some coordinates here, all right? But I kind of cheated when I did the, looked at the choices here, I'm like, all right, they're not going to be any, so just to save time, I'm not going to bother with that. Let's consider this point, which is the vertex of the parabola, all right? And that will basically be what sits here and here. Okay. The vertex, if you were to read the graph, appears to be at the location of 4, 3. So you would place a 4 here and a 3 here. So in the most concise way, without using this y-intercept and potentially these x-intercepts to calculate what a and b are, this is what you would get. Negative x minus 4 squared plus 3. Of the 4 or 5 choices, that would be choice A. Okay. Remember that this is always counterintuitive. If you see a negative 4, it really means positive 4. And the y value is a little bit better. We are at the hour-and-a-half mark. Oh boy, that's a bad blue. Another bad blue. Oh, shock. Section 1.8, it asks you to multiply 2 functions. This is problem 12. That's very faint. Okay. I think I might put this aside just not to be aggravated. And there's a new one. Okay, in the case of 12, they give you 2 functions. Wow, that is even worse. Function is equal to x squared, and then the second function is 7x minus 7. If you were to multiply these, they imply that by drawing this. The first times the second. A maybe more intuitive way of reading that would be to look at it like so. F of x and then g of x next to it. These are 2 different ways to say the same thing, multiplying. Okay. So, no sweat in that. The first one is x squared. Just pay attention to the right side, x squared. And if this is 7x, I'm going to sort of write it in the traditional way. Distribute this to each of these. You'd see that this is 7x cubed minus 7x squared. For 13, they ask you to evaluate the function using negative 5. So here's your first function, x squared plus 2, and then g of x. The second function is x minus 6. And then to specify, they want you to subtract the 2 functions and then evaluate using negative 5. Again, just pay attention to the right side of each of these. If this is f, we'll write that first. So this is x squared plus 2. minus, because it's a subtraction, and then x minus 6. I would simplify it first, distribute the negative, combine the like terms, and then evaluate using -5 just once rather than twice. So if you distribute the negative, you'd end up with this: x squared plus 2 minus x plus 6. And that would make this really x squared minus x plus 8 plus. Because it's +2 and +6 combined, somewhat ironically. Then if you insert -5, it's wherever there would be an x. So you would stick a -5 here and here. In the case of squaring it, it becomes +25. In this case, this is a double negative and it becomes 5, and then there's a +5 here. So this is 38. The last is a composite function. A composite function is essentially a function within a function, one inside the other, and it doesn't matter which is written first. So if you saw this rather than a dot, a hole, understand that it means a function inside of a function. And these are the two that they're asking to compose. Right? The first f of x is x squared. The second g of x is x minus 2. So if it is in this arrangement, this means essentially that the g function is inside the f function, which you might illustrate like that. If it was g in front, then the g would be on the inside and on the outside, and the f on the inside. Alright, so you know what helps? Writing it in different colors. G, x. Okay, so I'm going to write this half of the equation first. And then in place of this, I'm going to insert this half, x minus 2. And then because you end up with binomial squared, this is going to emulate the perfect square trinomial, right, which means that the outsides will each be squared, and the middle would be double the outsides, and those would be the sides. Now if you feel more comfortable, write it out. This will be x minus 2 and x minus 2, and then FOIL it. X times x is x squared. X times -2 is -2x. -2 times x is -2x. Together these become -4, which is the same as this term here. And then -2 times -2 is +4, which is what this is. So x squared minus 4x plus 4. And in this case, they didn't ask you, they just gave you the choice of x minus 2 squared, but I simplified it, or expanded it, arguably. Okay. All right. Then there's inverses. Okay, 15, find the inverse. There's a procedure to this. The inverse of the function 3 x cubed minus 4. Okay. Here is the procedure, which you can deviate from a little bit, but it's given in function notation, right? Italicized fx. What I would do is change f of x to just read it as y. So if it says f of x equals, make it y equals. Number 2, solve for x instead. In other words, rearrange it to solve for x. 3, then you're going to swap x with y and y with x. And then you're going to change the y value into function notation that looks like this. This implies an inverse. It's not an exponent. It's just a shorthand notation for that. An interesting thing about inverses and the functions they are inverses of is that they are symmetrical about the diagonal line y equals x. Virtually always. Anyhow, let's start with this. I'm going to change this to be y equals x3, x cubed minus 4. Right? I'm then going to solve for x, which means I'm going to have to move 4. That's very faint. That's too faint. Lousy markers. And 4 here and here. There's a cancellation effect naturally. And then you have, what is it, y plus 4 is equal to x cubed. In order to solve for x, you have to have x degree 1 perform the opposite operation. The opposite of cubing is to cube root. And in order to get away with this, I have to do it to both sides. So that leaves me with x is equal to the cube root of y plus 4. Now I'm going to swap the x with the y. So if it says x here, I'm just going to call it y. And if it says y here, I'm just going to call it x. And then the last thing is I'm going to write this in inverse notation here, which means that the cube root of x plus 4 is the inverse of the original. These are inverses. There's my math ant again. Dude, you're going to get hurt. Right. If you have a graphing calculator, you don't really need to do this, but you'll see the fun fact illustrated that inverses are symmetrical about a diagonal line that would be exactly y equals x. Right? And if you plug in the original one into your graphing calculator, you will see this, minus 4. And if I plug in the inverse, the cube root, x plus 4, I have it typed like so. The cube root, which I got through the math button, of x plus 4, and then the original function here, x cubed minus 4. I may have to adjust the screen dimensions, but if you hit graph, here is the inverse, drawn first, and here's the original function. Now, it's a little out of whack just because the screen is rectangular, so it's distorted slightly. So what I'm going to do, a couple of things. I'm going to change this so that it's z squared. It'll make it a little bit more correct. Okay, now, if what I'm saying is true, that these are symmetrical about the line that is diagonal y equals x, I'm just going to draw that superimposed on it, and you'll see it goes right through the middle of them. That's beautiful, isn't it? It's kind of a nice, it looks like a bug actually. Hey, math ants, where are you? You know, I drew a picture of you. All right, anyhow, that is a 45-degree line y equals x. Okay. It's a way to verify graphically that in fact you have drawn the inverse, or you have calculated the inverse. Okay, that would have been the end of the first test. I'm going to go a little bit faster now. This information that follows it is based upon that. And let me get a sip of water, so I'll be right back. All right. Blue is trouble. Black. That's better. Okay. Section 2.1 and 2.2. I put some hints on the test that suggest, you know, the model that you have to create. Pardon me. For 16, it says convert from from general form to vertex form. This is a quadratic function in general form. Which is unfortunate, because if you were to refer to something as not a function and just simply refer to it as an equation, when they talk about this, imagine this was just 0 equals this, an equation as opposed to a function. It would be referred to as a standard form of a quadratic equation if it wasn't a function specifically. When we designate something a function, then they use the word general instead. Reason being because they have this word that is standard form, which looks like this, also known as vertex form. A x minus h squared plus k. It's a derivative basically of the transformation model. These are the location of the vertex of the parabola. And if you wanted to calculate those, realize that h is standing in for x, the vertex x, and you would calculate that from this formula, negative b over 2a. K is a stand-in for y in the vertex, and that would be the function evaluated using the h value. There's a formula for this as well, but it's more trouble than it's worth. Anyhow, if this is general, then this is A, this is B, and this is C. So, steal the A, steal the B. Insert them in here. 4 and 2, and straighten out. It's negative 4 sitting on top of 4, which is what? Negative 1. So in place of A, you're going to stick negative 1. And then, pardon me. No. Get ahead of myself here. In place of H, you're going to stick negative 1. and we'll come back and straighten it out. As for k, k is the original function evaluated using h. So if it's 2x squared, and that really is an x value, it's 2 times negative 1 squared plus 4 times negative 1 minus 4. And then you go about your business, figuring it out. Okay. This is really 1, so it's 2. This together is minus 4, and this is a minus 4 that's there, working left to right. This becomes negative 2 minus 4. This is a negative 6. So in place of k, I'm going to put minus 6 in my model. The last thing is to get a. The easiest thing in the world is to simply take it from the original equation and write it there, which means that this is the same equation in standard k vertex form. I should let me correct myself. This is the same function, all right, in standard form of a quadratic. So you would see 2 times x, a double negative, is plus 1. It is squared because that's the parent function. And then this is minus 6 on the outside. My back hurts. All right, problem 17 is doing the exact opposite. Converting from vertex form, I'm sorry, I'm boring myself, standard vertex to general. So if you are given this, the function is equal to negative 2 times x minus 1 squared plus 2. Just perform the arithmetic. Order of operations to straighten it out, right? And then put it in descending order. So in this case, you would have to square x minus 1. That's going to end up being the perfect square trinomial. But if you feel uncomfortable with that, do the actual FOIL, you get the same answer. This is a negative 2 here, this is a positive 2. Once you have it in the factored form, you could, if you want to, introduce 2 to each of these things or do it as an afterthought. I would want to combine these things first, that's just me. All right, anyhow, it's going to be x squared and minus 2x and then plus 1. And then if you have a negative 2 sitting on the outside, distribute that. This still is plus 2 here. You would end up with negative 2x in the front, plus 4x minus 2, and then there's this plus 2 hanging on here. And you combine whatever like terms that you are capable of, and these x's would cancel. That means that you'd be left with this as the function. Negative 2x squared plus 4x. Technically, if you wanted it to make it simulate the general form with a constant on the end, you could put plus 0 if you really wanted to be that particular. Okay. Alright, 18 says find real zeros. Real zeros are just a fancy way of saying the x-intercepts. So if you look for x-intercepts by sticking 0 and y, the real zeros would be the same procedure. I did put some hints here if you wanted to graph something. I didn't ask you to actually do that, but these other things on the side in purple on the sheet, right? Like the number of, this is just little intricate things. If you wanted to draw a picture, all right, the number of real zeros is equal to the degree of the polynomial, pardon me, it's less than or equal to that. So if in this case you end up with a function is equal to negative 2x to the fourth plus 2x, this is similar to the previous problem but not exactly the same, 2x squared. The degree of the polynomial would be the highest degree available here. So if this is a 4 here, then the number of real zeros that you can expect would be something exactly 4 of them, exactly 4 or a little bit less than that, right? So expect 4 or less real zeros, aka x-intercepts. How do we go about doing that? Well, if it's an x-intercept, this is really a y. We call this 0, and then we factor this. This will factor pretty easily. Right? It ends up factoring like this. X squared minus 1. The GCF method would be the go-to method here. These are both composed of, the common factor is negative 2x squared. Negative 2x squared times x squared would be negative 2x to the fourth, and then times negative 1 would be the positive incarnation of this. You end up with something that is a difference of 2 squares. So this would end up being this completely factored equal to 0. This, when you have something completely factored, this is another little hint that I drew on the paper. You might refer to this in completely factored form as intercept form of a quadratic function when it's completely factored. It doesn't have to be set equal to 0, but that's what it's simulating. Now, the zero product rule is what we would employ to figure out what these would be. Remember, this is standing in for y. Each one of these, right, can be written as a teeny tiny equation unto itself. And that will give us what the real zeros are. In this case, you'd have to move the negative 2 via division. 2's would cancel, x squared would be equal to 0 nonetheless. Take the square root, both sides, x would be equal to 0. When y is 0, x is 0. So you would have a real 0, aka an x-intercept at the origin, in this instance. In this case, you would have to add 1, and x would be equal to positive 1. When x is 0, in this case, then x is 1. Pardon me, when y is 0, x is 1. All right, and in this case, you subtract 1. X is negative 1, and then this would be the third. Okay, which would be this. All right, notice that the y's are all 0 for your real zeros. All right. If again you were drawing a picture, that would help you flesh out the graph. Right, you'd have basically dots at those locations. Right, now getting back to what I was saying before, the number of real zeros, which I should have written, but I didn't. The number of real zeros, so just call it n, right, is going to be less than or equal to the degree. So if the degree is 4, right, it's got to be something less than that or exactly it. So expect 4 or less. How many did we get? We got 3, which is something less than 4. It kind of helps you to sort of predict what you're going to get. Anyhow, you would have a dot at the origin. you would have a dot at the location of +1 and a dot at the location of -1. Right? That's these three real zeros. Okay, the last thing I put is a mention of multiplicity. I just erased this to clarify that point. Multiplicity is the degree of each factor. Right? And the reason that a person would care is that based upon whether you have an odd multiplicity or an even multiplicity is odd multiplicities are a point of where the graph crosses the x-axis. Meaning, in this case, I erased it, unfortunately, so I'm going to have to put it back. Let me put it back. What was that? And it's a pocket protector. Just committed and jumped off the deep end here. Let's see, let me just put this back for a moment. I'm sorry. This is the function that we had to begin with. -2x to the fourth, yes. 2x to the fourth plus 2x squared. That's as it was given. This is it in the sort of intercept form. X, which is this. -2x squared, x minus 1, x plus 1. This is as it was given. This is in the intercept form. Note the degree here of this term. The degree here is not written, but I will fill it in. Okay. In the intercept form, the multiplicity is exposed. That is the degree of each of the factors. I know that there is no parentheses here, but just to illustrate, I'll put one there. When the degree of the factor is odd, as it would be in this case and in this case, that particular real zero is going to cross the x-axis. That makes it a little bit easier to see. Because they are odd numbers. It's x, this is degree 1, and 1 is an odd number. This is degree 1, 1 is an odd number. So that particular dot, that's this one, and this one specifically, the graph is going through those. When you have an even, the graph, you might say, bounces, or some textbooks they say touches. I like bounces personally. X-axis. That's this one. To touch would be to do something like that. Right? It wouldn't go through. Right? It would either from the bottom or from the top. Okay. Okay. Now, just so happens that problem 19 is asking you to find the number of turning points. Is the next thing. I'm going to leave this drawing here. The number of turning points is less than or equal to the degree of the polynomial minus 1. So in the previous problems, we're using the same thing. This is 19. The number of turning points, which I'll just call n still, is less than the degree of the polynomial, which is still 4, but 4 minus 1, which means what? It means 3. In this case, when we're referring to the turning points as opposed to the number of real zeros, what you should expect is 3 or less turning points. Turning points are where the graph switches, right, from increasing to decreasing. So if we expect 3 or less, that means it could be exactly 3, or it could be 2, right? Looks like that's what's going to happen here in this scribble that I drew. Again, you weren't responsible for this, but if you wanted to, you could help flesh out a graph with this information, all right? We have the real zeros, those are the points along the graph that are the points of the intersection or touching the graph, x-intercepts. And then it has to curve down the graph like this. Now there is one other thing I left out, and that is basically how you can decide whether something is increasing or decreasing or not. A couple of things to bear in mind. In other words, the end behavior. I'm really belaboring the point, but the end behavior is basically the direction of the arrows. You could kind of predict that now anyway, but it might have started with that. Arrows pointing up, arrows pointing down. If you have a parent function that is even degree versus odd degree, under normal circumstances, even degree has end behavior like this. Upward pointing arrows. And in the case of an odd degree, you have kind of one of each. On the left side, you would have a decrease. Oh, it is technically headed. If you read left to right, that's how you would read it, but it would be pointing down here and pointing up there. Now, in the problem that was given to you, this again is the function. The function is negative 2 x to the 4th plus 2x squared. This is an even degree. At least that's what the parent would be. And that has the most bearing on the graph. There is a dip here because of the other features, but on the whole, it would be pointing up, right? It just so happens that there's a negative coefficient here. When you have a negative coefficient, lead coefficient, that part of the leading term, that has the most bearing on the graph, which is why in this instance you have a picture that looks like this. You have a downward pointing arrow this way and this way overall, right? Then there's the second term, which is still even, and it should still be pointing up like this. That's why there's this curve here. It's kind of fighting it. It's like it's downward pointing, and then in the middle it's kind of upward pointing. Okay. Up, down. This is a negative coefficient. This is a positive coefficient. All right. Either. Okay. All of the blues are lousy, but at least I know which one writes nicely. Okay. Let's see. 20 is to use polynomial long division or synthetic division if it's conducive to that, and to find the quotient. Now, in the case of 20, I'll do it the more brute force way because it works 100% of the time. But if you have something given to you like this, 2x cubed plus 5x squared minus 4x minus 5, and it's being divided by x plus 3. This is a good candidate for doing using synthetic division. All right, I'll do it both ways. Regular long division and then synthetic. Long division is more arduous, but it works 100% of the time. You would put the divisor naturally outside of this little division house. If there are any missing terms, there aren't in this case, you would fill in a missing term with 0. Right? And don't feel bad about throwing in things that aren't there. Like for example, if the x squared were missing, if it just jumped from x3 to x, you would put 0 as a coefficient and then x2 just to fill the void, because it makes the intricacies of this work that much more easy, less difficult. Anyhow, this is a repetitious process. I'll try to limit myself to this much space. It's the first divided by the first. 2x3 divided by x. The result of this is 2x squared. Put that in the solution. You're going to subtract, but you're going to end up subtracting two things, and I'm going to have to distribute a negative as a result, so group that. There'll be something here and something here. You arrive at that by multiplying the quotient times the divisor, just like normal. Normally it's just a number here and just a number here, but in order to figure out what goes here to subtract, you in theory would multiply these two things. So 2x squared times 2x times x is 2x cubed. That's the first one. No coincidence that it exactly imitates what was there. And then when you distribute this, it would be plus 6x squared. So I'm going to put plus 6x squared. I have to group these things into parentheses because they're both being subtracted. So in theory, this negative would affect this. The result now is that the first terms cancel. They will, if you're doing this right 100% of the time. Distribute this negative. This is really minus 6. So it's 5 minus 6, which means negative 1x squared. Then you drag down negative 4x and you repeat the process. So it'll be the first divided by the first. Negative 1x squared divided by x is just negative 1x. Put that in the answer. And once again, you have to figure out what are the two things that you're subtracting. negative 1x times the divisor, x plus 3, distributed, negative 1x squared. It might seem like overkill, but I like to put the coefficient for this purpose. And this is minus 3x. Now what goes here and here are the things I just calculated. Minus 1x squared minus 3x distribute. A negative and a negative is a positive. This is going to cancel out of existence. A negative and a negative is again a positive. This is really negative 4 plus 3, which is negative 1x again. One more time. The first divided by the first. The x's cancel, it's negative 1. Put that up in the answer. Okay. Negative 1 times x plus 3. Distribute is negative 1x minus 3. That's what goes here. Negative 1x minus 3, grouped into parentheses, subtracted. A double negative is a positive. These cancel. It happens again. This is a positive. It's really negative 5 plus 3, which is negative 2. Since you're out of things to bring down, this is the remainder. And just like an ordinary division, what you would write is what you have in the quotient here. So you would have 2x squared minus x would be less complicated than putting the coefficient, minus 1, and then you could put minus 2 over what you divide by, x plus 3. It's an ugly fraction, if you will, right? It's sort of like when you convert an improper fraction to a mixed number, right? Whatever you divide by, that's the denominator of the fraction. So it's just an algebraic fraction, if you will. This is the answer. This long division process is a little complicated, especially with the sign changes, but right, it works 100% of the time. Right. So alternatively, if you could have factored this, and then it just by coincidence had that as one of the factors, you could cancel with it. It would be dividing without consciously thinking it. Anyhow, if you want to, you could rewrite this as plus a negative, like that. Sometimes that's what the answers say in the book. It is exactly the same thing. It's just putting the negative here versus there. All right, now, synthetic division is something that you reserve usually for just a situation where the divisor meets some criteria. You could get away with doing it in a more complicated problem, but you really wouldn't want to. It has to be linear, which is implying that it is degree 1. It is. And the lead coefficient also has to be 1, which it is, right? And then what you do is you take your positive 3 and you switch it to negative 3. So if it was a negative 2 to begin with, you'd make it a positive 2. And you fill in a little table. The table looks like this. There's a box here. And there's a box here to designate the remainder. And you just incorporate the coefficients in this. So if it's 2, positive 5, negative 4, negative 5, you would put plus 2, plus 5, minus 4. I should space this a little bit better. Start from the far end, negative 5, minus 4, plus 5, 2. Right? I really should have put the sign. This negative 3, again, it's the opposite of whatever is here. You put minus 3. You systematically, I put this way off. This is very far away from what it has to be. Here. You systematically drag these down and then multiply instead. That's why it's called synthetic division, because you're not actually dividing, you're multiplying. You're rigging the situation to accommodate by changing the divisor sign, that term of the divisor. Negative 3 times 2 is -6. Do the arithmetic. One of each sign, subtract. This is -1. Repeat. This times this is +3. One of each sign, subtract. You get -1. Coincidentally, multiply again. Put it here. -3 times -1 is +3. You end up with -2, and this is the remainder. Then you go 1 degree lower each term. So if the original degree was 3, then when you're attaching a letter to these coefficients, it's 1 degree lower than 3. So you're going to start with x squared. And then it's minus x to the first, technically. And then it's 0, where you wouldn't bother writing it. And then you have the same remainder, -2 over what you divide by, x plus 3. Okay. Same answer, and just a preference of maybe putting a positive here instead. Okay. Okay. 21 is find the quotient of the complex number. Okay, so in this case you have 2 plus 3i sitting on top of 4 minus 2i. A couple of things to remember. Complex numbers are generally thought to be composed of a real term plus or minus an imaginary term. And the imaginary term is designated by the letter I. Now, what is imaginary? An imaginary number is something that has the factor of the square root of -1 in it. And since you can't find the square root of a negative because it doesn't have identical factors, one would be positive, one would be negative, to make it negative here. Rather than throw it away, what they do is they put an I out in front of the radical to go, well, it's imaginary, just remember that. Anyhow, you can't add imaginary numbers to real numbers. You can only combine like things. Real could be added to real, and imaginary can be added to imaginary or subtracted. But just remember this. If you take the square root of 1 at that point, it would just be 1 with an I. When you have a denominator that incorporates an imaginary number somehow, and again, they would refer to this sort of collectively as some combination plus or minus of these two parts, a real 4 and an imaginary 2i, you have to do something similar to the situation of having a radical in the denominator, which is to rationalize the denominator. Which is, for all intents and purposes, it's to just simply manipulate what's given to you so that the imaginary number does not show up there. Right? You will have an equivalent expression, it just as the parts rearranged. Right? It looks nicer. How do you rationalize the denominator? Essentially, you're going to multiply by a convenient ratio of 1. Multiplying by 1, both parts, is not going to change the value of something. It's just, if it's a convenient incarnation of the ratio of 1, it will be disguised essentially. It's going to manipulate the appearance of it. The aesthetic will change, not the value. So what that amounts to in the case of complex numbers is to employ a complex conjugate. A complex conjugate, if you normally have two things, again, a real part A plus or minus an imaginary part, B, with an I attached to it. The conjugate of this would be the same terms with an opposite sign between them. So I'm going to form a ratio here that is equal to 1 overall, but the top and the bottom is going to be the conjugate of this unique thing. So if it's 4 minus 2i, the conjugate of this would be 4 plus 2i. And as long as I do it to both the top and the bottom consistently, it is a ratio of 1. It's ugly, complicated, whatever it is, but it still amounts to 1. So in theory, the value of this will be preserved. It will just change the appearance of it only. So, let me get rid of the unnecessary gobbledygook here, and we will multiply. Treat them as if you were foiling. First times the first. That's 8, right? Is that visible? Looks like it is. 2 times 2i is plus 4i. 3i times 4 is plus 12i. And then 3 times 2 is 6. And then I times I is I squared. Now this extra little fun factoid here will come in handy later. If I represents the square root of -1, then I squared is to square this, which would make it the amount of -1 more or less exposed. So wherever you see an I squared, you could put -1 when you get there. You would try to combine what you can. Again, imaginary combines with imaginary, real combines with real. So the top here would condense down to this. It would be 8 plus 4 and 12 is 16i, and then it would be 6 times -1, because I squared is really -1. That means that it is 8 plus 16i minus 6. And then to tidy it up, combine what is real with what is now real. You put the real term in front. This would be 2 plus 16 with an I. Now, people often ask, like, do I have to put the I in the front or behind the number? My preference when I don't have a radical is to put the I behind the number. When I do have a radical somehow, then I would put the I in the front, just not to make it look like it's under the radical. Anyhow, all this is just going on top here. 2 plus 16i. Back hurts. Did I do something wrong here? Let me just double check my arithmetic. 8, 2, 12, 6, right? Yeah. Looks like it is. No, it's fine. Good. All right. Just being anal now. All right. What's going to happen when you foil essentially the bottom now is that it simulates the conditions of the different, I'm running out of space, but like what's going to happen when you do this? When you distribute each term to each term, it's going to be the same outcome essentially as the difference of 2 squares. So if you happen to have that model memorized, you can predict what the end result is going to be. But I'm going to go through the intricacies of this. 4 times 4 is 16. 4 times 2 is 8 with an I attached to it. -2 times -2 times +4 is -8i. This is why I say it's like the difference of 2 squares. The middle terms are going to cancel. -2 times +2 is -4. And I times I is, once again, I squared. If I straighten this up a little bit at a time, these terms will cancel. This would be 16 here, minus 4, and then I squared is -1. which means that this is going to be 16 plus 4, which means that this is really 20. The results that we get, I'll put it over here, is this. It's 2 plus 16i above the line and 20 as the common denominator. A lot of times, although that is fine and you could simplify it, you could factor the top in theory. What they do is they separate them out. Right? If this is the common denominator, that's the real fraction. And this is the imaginary fraction. So what you end up with is 2 over 20, which is going to be really 1/10 if you simplify it, plus 16 over 20 with an I attached to it, and you can simplify that fraction. So they're both divisible by 4. This is 4, this is 5. So you'd have 4/5 I. That would be the best answer, arguably. 1/10 the real portion plus 4/5 the imaginary portion. So much time just erasing. It's one sucky thing about having a board that's only this wide. You have to constantly erase it, which is why it takes me 3 hours to film something. Alright, up to 22. We're getting near the end, eventually. 22 is solve the system of equations either by graphing, substitution, or elimination method. Just to summarize, alright, when you're asked to, this is 22, when you're asked to solve a system, you could do it graphically, you can do it via substitution, which is what I think most people probably do, or there's a third method, elimination. And there's technically a more complex version of this Gaussian elimination, but we're not going into that. Graphically is to pretend that you have two y equals, and then draw them and look for the point of intersection. y1 and a y2 graph. The solution is the point of intersection. When you substitute, you're basically plugging half of the first equation, perhaps, into the second equation. Right? And then eventually back substituting. The elimination method is the most involved, but it's interesting. It's basically changing, it's writing equivalent. Equivalent equations that cancel one letter. This involves multiplying, you know, like just consistently all the terms, both sides of an equation to change the appearance of an equation. I'll try it a couple of ways. The substitution method is probably the fastest in this case. So here, if this is the system, I think that textbooks should write systems very nicely and to make it as clear as possible. But if you see fancy brace like a sandwich just on one side, that designates a system. The system is two or more equations sort of stacked. So just designate one, the first and the second. I circled these 1 and 2. The actual equation is x minus y equals 0 on the top here. And the second one is 5x minus 3y equals 6 in the second one. Right. Again, the substitution method is probably the go-to method. Right. And when you have harder problem, it's not easy. Right. If you had a third equation, I would not necessarily use the substitution method. Gaussian eliminations, or matrices is really what you would end up doing. Anyhow, let's rearrange to solve for x. If I add y to both sides, then the result here is that x is equal to positive y. All right? I'm going to stick half of this first equation into the second equation. That's half of it right here. In place of x, I'm going to stick with x equals, which is y. That eliminates a letter without really consciously thinking about it. And the result is that you have like terms, 5y minus 3y is 2y, and that's still equal to 6. And then you could solve for y, divide by 2, and then y is equal to 3. And then you're going to back substitute. You can go to any incarnation of the formulas, but you might just go to this one here. If y is equal to 3, what is x equal to? There's no extra features. X is equal to 3. All right? That is the solution. Right? If you wrote it in the style of a coordinate, x comma y, it would be the point 3 comma 3. Now, if you're going to go about it the graphical way, which would be cool if you had a calculator, or you had graph paper at the very least, you'd have to rearrange these each so that they're y equals. Right? The first one already is. All right, if the first equation rearranged to solve for y would be y equals x. The second equation rearranged would be a little bit more complicated. Because it's 5x minus 3y equals 6. You'd have to manipulate a lot. Minus 5x cancels. Negative 3y is equal to negative 5x plus 6. I'm putting it in the sort of y equals mx plus b standard. Divide by negative 3. This second y, this is the first y, is 5/3 to the slope minus 2. If I graph these, they're going to cross at that point, 3, 3, the solution. I'll do that really quick with my graphing calculator since I don't have graph paper. And I'll clear out my old junk in here. Right. In the case of the first y, I'll make it just equal to x because it's just thankfully not that complicated, x. And then in the second one, I'll incorporate a fraction here. So I like to put it in the intuitive style of writing it. Minus 2. You don't have to put it in the obvious top and bottom 5/3. You can make it /. Just be careful. I would put parentheses if you don't do it this way. And now hit graph. And this is the first line, y equals x is a perfectly diagonal line. And here is the second line. Now you could, if you want to, fiddle around with the zoom feature. Zoom fit would probably be the nicest way to write this. Zoom fit. Nah, it's funny doing it backwards. Or you could hit, nah, that's not much better. Disappoint me, zoom. I'm gonna put it back. I'm gonna zoom in, all right? Okay, that's just slow. If you hit zoom in, just beware. You have to press the button twice. That doesn't do anything, but if you hit it again, you'll see that it zooms in literally. It's a little off though, so I'm going to back it off again. Zoom out. Sometimes it's more trouble than it's worth. Anyhow, you see that they cross. You could try to finagle reading that. If you hit trace and then you already happen to know what the x is, if you press 3, it'll tell you what the y is, 3, and it's right there. If you're not satisfied with that, hit second and then trace to get the calc feature. You could opt for intersect. I'll ask you a bunch of silly questions. Is this the first curve? Technically, yes. It's not a curve, but yeah, whatever. So you go, yeah, and then it tells you 3, 3 is the intersection. The elimination method is, a powerful technique. And really, if you were going to go the whole 9 yards, incorporating Gaussian elimination, that's really if you have something that is, like 3 equations versus 2. In which case, you'd probably just employ matrices, linear algebra. It's doing this. It's changing the appearance of what you have. This is the original equations as they were given. So that you're going to change the appearance of this such that you're going to subtract a letter out of existence. This is how the system would be ideally given to you. This is the first thing, this is the second thing. Imagine this as being a big table, and these are columns. And you were going to blend together the parts from one with the other. Normally you wouldn't dare do that, right? But you can, right? Just via whatever their signs are. In this case, it would be 1 plus 5, and you'd get 6x. In this case, it would be 1 and 3, and you get negative 4y. And this would be 6. And that wouldn't be helping you, right? You end up creating one unique line, all right? But that's the idea, to blend together the parts from here and here in a way that one of these goes out, just cancels out of existence. So what you would do strategically is pick a letter, a variable to cancel, doesn't matter which. One might be easier than the other. And then multiply by a factor that would, I'm trying to think of the word, facilitate cancellation. If you wanted the y's to go away, what would the digit here have to be? It would have to be a positive 3 because this is a negative 3. So what you would do is you might grab this entire thing and multiply by negative 3 here for the sake of consistency, here because this is what you're really after, and then here again for the sake of consistency. And what you would get is negative 3x. A negative times a negative is a positive 3y, and then 0 times that would be 0. And then beneath this is still what was there, 5x minus 3y equals 6. In this incarnation, the blue incarnation of number 1, when you attempt to combine these will cancel out of existence. It's elimination of a variable without maybe consciously thinking about it. In this case, you have one of each, you end up with a positive 2x, and in this case, you just have a 6. And this is the same problem from substitution before. Divide by 2, you get x is equal to 3, and then you back substitute. Stick this into any version of these equations, this 3, and you will figure out y. Y is equal to 3. The hard part is choosing which letter to cancel, because depending upon the problem, it might be easier to do it one way or the other, and you only know as a result of experimenting with it. Anyhow, this is the most concise way as I could refer to it. Multiply by something. In this case, I'm multiplying by negative 3 because that facilitates cancellation. It causes cancellation effect further down the road, further down the train of thought. Okay. So that's 3 ways to do the same thing. I'm gonna get a sip of water and maybe do some yoga because my back hurts. Because I'm having to lean. Alright, 23. Alright, I purposely made 23 a multi-step process to walk you through the having to draw something by hand, specifically a rational function, because to me that's the creme de la creme of drawing functions. Okay, so here's my marker here. Blue. Okay, 23. This is the function that's given to you. It is a rational function because it has a denominator where the variable exists in some form. So remember the parent of this. The most basic type is something no more complex than that. Remember, which is another way of saying x to the negative first degree. In terms of a graph, they look like this. And they have 2 points that are interesting to the graph. 1, 1, and negative 1, 1. They don't touch the origin. As a matter of fact, what they have is a vertical asymptote and simultaneously a horizontal asymptote, which would technically be at the origin. And now it's not part of the graph, it's a boundary where the graph doesn't exist or where it's undefined. Okay, anyhow, so this is more complicated than that, but it's just really just an amped up version of this. So you're gonna see similar looking curves predict ahead of time. All right, now, how would you go about fleshing out the graph? There's multiple steps here. I made it the whole page here, right, to walk you through the process. Right? I'm gonna sort of draw cheesy coordinate plane here, and try not to get in the way of my own writing. Okay, this is x, this is y. Okay, so here's A. First thing is, let's find the y-intercept. The y-intercept occurs where x is 0. You're going to stick a 0 in place of x. So if I take this and do this, put a 0 in the top, 0 squared minus 0 minus 2, that's what y equals, because this is another name for y. You end up with a 0 on top and a negative 2 on the bottom, which is really just 0 anyway, which means that in this case, there's a y-intercept at the origin. That means that there's definitely going to be an x-intercept in the exact same location. That one is always a given. Okay. Save that information, put a dot there. B. Change the color here. Put it in black so it'll be easy to see. Factor the top and the bottom, right? The reason that you try to factor the top and the bottom, and it's not too hard in this case, is that it will reveal where there will be holes in the graph potentially. They call those removable discontinuities, and or the asymptotes, which are the imaginary boundaries like this in the parent situation. So B, to factor the top, it's just x. You could put a parentheses around it if you like. The bottom, being a trinomial, would be something like this. X, and 2 and 1, and 1 is negative and 1 is positive. That's as it would factor in this case. C is to check for the holes, all right? Removable discontinuities. Is another way of saying holes. Right. Removable discontinuities. They're removable because unfortunately once you have something factored, you might jump the gun and cancel out, for the sake of simplifying, a factor that occurs in the top and the bottom. But if you do that, you are unfortunately ignoring that there would be a hole. in this case, because there is nothing in the top and the bottom that resembles one another, there's no cancellation effect going on here. So that means that there's going to be no holes in this problem. All right. There's no cancellation effect. All right. But there'll be asymptotes for sure. So we'll check for those, which is the next thing. D. It ends up being that it's the denominator, right? The asymptotes are basically a trick of, how shall I say, looking for domain, right? And remember, for rational functions, when you look for the domain, it's the denominator that can't be equal to 0, because then it would be undefined. Well, we're looking for the places in the graph, namely the asymptotes now, where it would be undefined. So we're going to take the denominator's factors, which in this case are 2, x plus 1, and x plus 2, minus. And set equal to not equal to 0. It's more or less, again, this is a consideration of domain, and essentially the 0 product rule. Those 2 points. All right, so if you were to figure that this is not equal to 0, let's pretend it is for a moment, this would give you this teeny tiny little equation. And in this case, this would be a second teeny tiny little equation. And you'd manipulate each, and you'd say, well, x can't be negative 1. And in this case, well, x cannot equal positive 2. Right? It's at those locations, which are vertical lines, that you have vertical asymptotes. So at the location of negative 1, you would draw a dashed line like this. This is a vertical asymptote. And at the location of positive 2, you would put a second dashed line in this problem. That would be there. Those are boundaries where the graph would not exist. All right. For E, there are 3 rules. We're looking now for the horizontal asymptotes, because these vertical lines are vertical asymptotes. E has 3 rules, right? And I wrote them on this piece of paper here. Rule 1, 2, 3. Right? Rule 3 really is when you have a slant instead, but that's a special case. Examine the degree of the top and the bottom. The degree of the top is 1. I want to analyze the degree of the top versus the degree of the bottom. That is the numerator and the denominator, so-called. In this case, the top is 1. The degree of the bottom, it's always the leading coefficient, well, typically, is 2. What's their relationship? Equal, less than, or greater than in this orientation? Less than. That is basically rule 1 in this list, which means that the horizontal asymptote is in the normal place. Y equals 0. If the degree of the top is less than the bottom degree, then the horizontal asymptote is the x-axis. It's y equals 0. It's a horizontal line. A dashed line. So you would put a dashed line in here. Okay. Now let's get some x-intercepts. And I'm running out of space, so I'm going to go back up here. The x-intercepts, this is part F, if you will, is just paying attention to the numerator. this equation equals 0. The reason that you only have to pay attention to the numerator, right? Because normally when you have x-intercepts, what does that imply? It means that you're going to take a 0 and stick it in place of y. What's going to happen is that the denominator is going to cancel out of existence. Well, it'll be multiplied by 0, essentially. If I put a 0 in place of y, and then take this and multiply it, you know, here and here, I would have to do the same thing to the opposite side. It would cancel the denominator here, and 0 times anything would be 0 here. So realistically, you just have to pay attention to the top. And since the top is nothing worse than x, then that means that x is equal to 0. As mentioned before, if you have a y-intercept that is the origin, you're guaranteed to have an x-intercept as well that is in the same place, 0, 0. So this point here, already calculated, is simultaneously an x-intercept and a y-intercept. Okay, moving on. Look how easily that erases. G. All right, now G, you didn't really have to do this, but if you want to flesh out the graph, right, and you kind of know that it's going to look something like this because this is the parent, just realize that this is going to be a little bit worse because you have intervals going on here. There's an interval that stretches from here to here, and an interval that stretches from here to here, and then another interval from here to here. So what you might do is figure out first what the intervals are, and then strategically select an x input value, and then evaluate the original function to figure out what the y coordinate would be. So you might start with a table like this. Let's figure out what the intervals are. Strategically select an x, plug that x value into the function, and that will give us a y, and then pair them together to write them as a dot, like so. Let's figure out what the intervals are to start with. The interval that stretches from what would be negative infinity up to this line, dashed line, is this interval, from negative infinity up to the boundary of -1. And then the interval in between, at least, let's say that we went up, we'll be a little bit more precise, from here to 0. -1 to 0. It's kind of overkill, but so what. And then from 0 up to this boundary. So from 0 to +2, and then beyond, right? From +2 to positive infinity. There's a spectrum from this chunk that we want to figure out an x value that would be convenient to use. I'm going to erase a little bit because I don't really want you to think this is part of the graph because it's not. There we go. Messed with it a little too much, so I'm going to put back what's missing. This line is still in here. And this dash line is still here. Okay. Now, to make these a little bit darker, that's 0. This is negative infinity, and this is positive infinity. Let's choose an x value in this spectrum here. A good one to use might be something that fits in here would be maybe as small as possible. All right. If I can't use -1 because it's undefined, what's one number higher than -1? Well, lower technically. -2 I'll use. In this spectrum, from -1 to 0, that's more of a nuisance, all right? Because the only thing in between them would be a fraction. So in this little area in here, -1/2 I would have to use in that case. In this spectrum here, I can get away with using a whole number, +1. And in this spectrum beyond, from 2 to infinity, let's just go with 3. Try to use numbers, again, if you can be strategic about it, that are easy to get away with working with. You would have to systematically stick these numbers into the original function. And I scribbled on it, out of commission here. So I will rewrite it nicer. Here's the original function. It's f of x. For our purposes, we're going to call it y. X sitting on top of x squared minus x, was it +2? -2. It's very faint, but maybe better that it is. Okay. If I insert -2 in here, then this is what I would end up with. A -2 above the line. This would be 4 + 2 - 2. So you'd end up with -2 on top. This would be 6 - 2, which would be +4 on the bottom. And then you would end up with a fraction. You'd end up with -1/2. So the y value here would be -1/2. If you paired those together as a coordinate, it would be -2, -1/2. There's a dot at that location in this boundary, or this region here. So if this is -1, let's say that that much is -2. Because this is a negative fraction, it would be below the asymptote. So you will have to figure that this is a half. Okay. Again, if this is something like this picture, and there's no lead coefficient that's negative, to at least in the actual example here, in the original form of this, the curve would look like this, simulating our normal case. Right? Now, we have to calculate this in 2 places on opposite sides of this dot. And I would plug in 1/2. That's more of a pain in the neck. All right? But if I did it again, if this is y is equal to x sitting on top of x squared minus x minus 2, and I now insert -1/2 here, here, and here, it's a little cumbersome, but the way it would work out is this. The top is just -1/2. This squared is +1/4. This is +1/2 because of the signs, and this is -2. Let's make this a common denominator. This is 1/4 plus 2/4 is 1/2, and that would be 3/4, and then 3/4 minus 2. To make 2 conducive to working with a fraction here, let's make the denominator 4. It would be 8/4 is the same amount of 2. So what you would end up with is -5/4. Yep, that's what it is. -5/4, right? Sitting underneath this 1/2. -1/2 divided by -5/4. Keep change flip. -1/2 times -5/4. A negative times a negative is a positive. This would simplify to 2/5. So your fraction would be a terrible fraction, but it would be a positive. So you have -1/2, comma, +2/5. There would be a dot at this location. In between 1 and 0 would be a 1/2 in this direction. Above, because it's positive, 2/5, if that's 1, you'd have a dot roughly there. Okay. If you did the calculation again, And in this case, you stuck positive 1 in the top, and 1 squared, and 1, and minus 2. This will be easy. It will be 1 over 1 minus 2. This is 0. This would be negative a half. So at the location of positive 1, negative a half, you'd have another dot. Here's 1, right? In the positive direction, a half negative would be here. You'd have this as a curve in here. One more of these. 3. If you put positive 3 in here, it'll be 3 here, and 3 here. This is 3 on top. This is 9 minus 3 minus 2. This is 6 minus 2. This is 3/4. You'd have positive 3/4. It's sucky that you have a fraction, but this is where you would have a dot. Right? You'd have it in this region here. Positive 3, you would figure would be there. Above the x-axis, but not quite at the location of 1, would be a dot here. You'd have a curve that runs like this, and that would be your graph. The more dots, the merrier, because the more that fleshes out. Okay. There's a similar thing that you're going to see for the nonlinear inequality that follows this, but it will be a little bit faster. So for 23, pardon me, 24, solve the nonlinear inequality. I put into what would normally be x-intercepts are key values that divide the number line into intervals, similar to the last problem. Knowing these enables you to be, and there's a typo here, it enables us to be strategic in choosing test points. So for 24, if it says solve, and this is what you get, x squared minus x minus 6 is less than 0, right? We're going to figure out what x is basically, but realize also, since this is an inequality, there's going to be a spectrum of solutions, not just one number, right? And because it is less than, right? Less than 0, that implies that they would be negative. So a couple of things. We're going to kind of look for x-intercepts as we normally would. And that means that we're going to sort of pretend that this is a y. We're not really going to graph this in 2 dimensions, but normally when you're looking for an x-intercept, what do? You stick a 0 in place of y, right? And then you factor. So we're going to kind of do that. It's very faint, I'm sorry. Put that aside. I'm going to essentially pretend that what is the 0 here is like y, and I'm going to factor. Hopefully this is a little bit more legible, ever so slightly. Treat these as kind of like x-intercepts, sort of. Right. Not really, because it's an inequality, but let's factor this. If it's a trinomial, then it would be x here and x here. There's a binomial times a binomial. And it would be something like 3 and 2 here and here. Negative 3 and positive. To multiply the negative and subtracted a negative 1. Let's solve this teeny tiny little equation. And it really can't be equal to this, because it has to be less than. X minus 3 not equal to 0. This is more or less like the zero product rule. Something like that. That's the process. This is subtract. X cannot equal -2. And if you add 3, X cannot equal +3. Because if you put these in here, they're going to be exactly equal to 0, and that's not allowed because there's no equals in it. It's just less than. Let's draw a picture. Because again, we're going to get a spectrum. A picture is more helpful. Here's -infinity, here's +infinity, 0. At the location of -2, which would be here, let's kind of just put a boundary here, or a hole in the more traditional sense. And at the location of +3, there would be a boundary here. But since I'm doing it in 2 dimensions, I'm just going to put it as a hole rather than an asymptote. Okay, now what does that give us? A similar situation before, right? We have to figure out, what the X value would end up being in this interval, and in this interval, and in this interval. So we're going to draw a little table as before. I need this space, so I'm going to do this. Okay, set up a little table. We have the interval established. We'll choose strategically an X value. We'll evaluate to see what Y is. Or what the polynomial is, really. I just don't. It normally would be called Y, but it's not. And then we'll decide what the outcome is. What the sign outcome is, because remember, we're looking for this. We have 3 intervals, so I'm going to make 3 spaces to fill in here. Let's decide what the interval is from here to here. If it's stretching from -infinity up to this hole, that would be from -infinity to -2. Neither of those would be incorporated. Beyond it would be from -2 up to +3, and then beyond that would be from +3 up to +infinity, which is forever. Okay, hopefully that's not too faint, but it looks like it is. So let me just emphasize, this is the first interval, this is the second, this is the third, and we just want to analyze basically what the sign outcome is. Okay, let's strategically pick an X that fits in this spectrum that is not 2, but not infinity. The next number would be -3, right? So we'll evaluate at -3 and see if this is okay as a result of that. Then we'll choose a number in here. Perhaps 0 will be the easiest thing. And then beyond it would say, we'll maybe choose 4, right? +4. Right? If I were to stick -3 into this original inequality, would it still be true? Let's see. Well, -3 squared minus -3 minus 6, what do you get? 9 plus 3 minus 6. That's 12 minus 6. That's basically staying, in the end, it's saying this, that 6 is less than 0. Is that true? It's not true. It's not true. But the answer is that you'd have +6 is less than 0, which can't be true, which is a positive answer, right? So that's not going to work. We're not going to consider that as an interval for solutions. If we did the same thing using 0 now, that would be super easy, right? If it's 0 squared minus 0 minus 6, let's see if that's true. This is false. All right. 0 minus 0 minus 6. The result of this is that negative 6 would be less than 0. Is that true? It is true. All right. Negative 6 is less than 0. All right. And the outcome, even more importantly, is a negative. Okay. Last one. If I did it again using 4, right? Negative 4 squared minus 4, that's positive. And then minus 6. See if that's true. This would be 16 minus 4 minus 6. 16 minus 4 is 12. 12 minus 6 is positive 6 is less than 0. Which is not true. False. And the answer is a positive. So this would be a dud as well. The spectrum of solutions is this spectrum. So if I were going to draw that, well, first of all, as an interval, it would be negative 2, positive 3. If I were going to draw this a little bit nicer on here, it would be like this, a curve in the middle of a hole, and a shaded line in between. This is where the solutions lie. Okay, the interval of negative 2 to positive 3, not including either of those two things. All right, well, that's the end of chapter 2. All right, we're at the 3-hour, 18-minute mark. Oh boy. Okay. I'm gonna turn the light now. These will be a bit quicker. Right. Chapter 3, for 25, it says use the one-to-one property to solve the exponential equation. If you have 8 is equal to 2 to the 2x minus 1, and you're using one-to-one property, that's this. One-to-one property for exponents is to suggest if they have the same base, if these are the same, then what you really can just say is that this is an equation of x equals y. In this case, we would have to interpret this 2 as to make it a same base. So this could be rewritten as 2 to the 3rd. And then we just have, okay, same bases, it's 1 to 1. Then this is the equation. Add 1 is 4 is equal to 2x, divide by 2, x is equal to 2 is the answer. That's 25. (26). Evaluate the logarithmic expression by converting to exponential form. Right. What I would suggest you do is convert this from logarithmic form by choosing a letter that it's equal to. It's not an equation in the way that it's given to you. What you have for 26 is this. You have the log of 4, the log base 4 of the argument 64. So what you will do is just pick a letter. Right? I like x personally. And just call this equal to x. Right? And now, since you know that logarithms and exponential equations or pardon me, logarithmic expressions and exponential expressions are inverses, draw this jelly bean, right? That's the base here, that's the base as it would be in an exponential equation, okay? 4, 4. And read it sort of counterclockwise. It's now equal to 64, right? From this, you can infer what the x would be without a calculator. Well, 4 to the third, all right, would be equal to 64, right? Because it's 4 times 4 is 16, 16 times 4 is 64. So therefore, x is equal to 3. Here's 27. Use the one-to-one property of logarithms, right, to solve the logarithmic equation. I'll draw this first. You have the log of the arguments 2x plus 1 is equal to log of 3x. Okay, the one-to-one property of logarithms is if you have, again, same bases, if these are the same, then the equation simplifies to just the argument equal to the argument. That is the guts in here and the guts in here. Now in this case, notice they're not written, right? But they're the common log. They really are base 10. If they're not written, you would always assume that. They're common logs, as opposed to natural logs, which would be base e. Right? So therefore, the argument of the first, since these are the same, is 2x plus 1 is equal to 3x. You could do this more than one way, but the easiest thing is to drag 2x over here via subtraction. 1 would be equal to 1x, which is the same as saying x is equal to 1. Okay. For 28, it says use the change of base formula to simplify. If this is what you're given, the log of the argument y over the log of b, to remind you, the change of base formula is handy in a situation where you don't have software that's updated to accommodate. Right. Before, more recently, that the Texas Instrument calculators were updated to have, you can enter a log of any base, right? It just had log button and natural log button. You would need to change a base formula to get a calculator. It's an old calculator to do this. Now, this is the change of base formula. If you have any log of any base, I don't have to say base. I hate to use letters like this, but let's just call this x and y. I don't want to confuse it with the thing we're doing. I'll put an N here. I'm just choosing funny letters because I don't want to conflate it with the actual problem. Yes. It could be rewritten like this. If you're given any type of logarithm that is any base, right, and any argument, you could rewrite them as this ratio, right? That the argument of the original argument is more or less the numerator, the top, and the base is now an argument. As long as you are choosing, and I'll make this a different color to stress this, the same base here and here, this is perfectly legitimate. Now the reason that this question is saying, use the change of base formula, is because that would solve for x in a simplified way, rather than writing it as a ratio. So in other words, you're going to condense this into one logarithm. The question is, what goes here and here? It's more or less reading this backwards, right? If this is the top argument, then that will still be the argument here. If this is the bottom argument, S here, then that's the base, B. So you would put a B here. This is x equals that. Okay. 29. Expand the logarithmic expression using properties of logarithms. When they say expand, they mean factor it, which means that it'll be a bunch of things being multiplied in their own little parentheses. So, in this case, for 29, you have the natural log. I had to write it sort of sideways, but this is the way it would be a little bit more intuitively. The log of 2, the argument 2 over 27, right? Of the properties of logarithms that this translates from, if you want to, you can do this right immediately. A natural log, which is what you see here, natural, is log base e. So if you want to, you feel more comfortable, do it like that. Start with this. It's not necessary, right? It's easier, more concise to simply put natural log, ln. Anyhow, the quotient property of logarithms is that if you have a log subtracted from a log, that you could write it as a quotient. So if this is x and this is y, then you could write it like that. Now, that's condensing, going in this direction. We want to expand. And let me just point at something also as well. There's a handout in case you need it. That looks like this, that has properties of logarithms. Unfortunately, because it's daytime, you see that the back of this is coming through here. Anyhow, look at the quotient rule. And when you have something that looks like a quotient, 7, it's a difference. So, what I'm doing here is basically this. I'm taking this and writing it as the natural log of 2 minus the natural log of 27 to start with. All right, and you might say, oh, well, that's the end of it, right? Try to factor, right? This is a prime number of 2. It would be impractical to factor it into anything smaller than that. But something like 27 can be factored into 3 times 3, 9 times 3 to start with. And then even that can be factored into 3 times 3 times 3 into exclusively prime numbers. Now, then take advantage of abbreviations that you could use if you have an exponent instead. This would be the same as saying the natural log of 3 cubed, because it's 3 threes, 3 iterations, so 3 clones of 3. And this is still natural log of 2. All right. There's the power rule, property rule, same difference. The power rule for logarithms suggests that if you want, you could put this 3 up in front. So if you see an exponent here, put it in the front. which means that you have this. The natural log of argument 2 minus 3 times the natural log of 3. This would be the expanded incarnation of this. Right. Factor, right, into primes, right, mostly, or composites that would be impractical. Right. Well, primes in general. Right. There's even 6 you can factor into 2 and 3. Yeah, that's a composite. All right. Next one. Red. Okay. 30 is condense the expressions by using properties of logarithms and rules of exponents, technically as well. In the case of 30, you are given this. The natural log of e to the 6 minus the natural log of e to the 2. Right. There's a number of different ways to do this. If you're using properties, all right, this again is right off the bat, it's the quotient rule. All right, which means that if you have a difference, all right, then you can make it look like a quotient. Just like if you have a quotient, you can make it look like a difference. So this would be the natural log of e to the 6 over e to the 2nd. Right? Properties of logarithms have a quotient rule. Then exponents have a quotient rule as well. Pardon me. Logarithms have a quotient rule. Exponents have a quotient rule. The exponents suggest that when you have the same bases, you could subtract the exponents, right? To condense them, consolidate. If you subtract these, what's 6 minus 2? 4. Right? Dropping my things. Which means that this is the natural log of e to the 4th, right? If you want to write it that way. Then there's the power rule. The power rule for logarithms means you can put the 4 up in the front. So this ends up being this. 4 times the natural log of e. And then it just so happens that when you have the natural log of argument e, that this is really this, right? It's the log base e of e. These are inverses. And according to the inverse property, this is just 1. So 4 times 1 is just 4. The answer to 30 is 4. Okay. 31 is condense the logarithmic expression by using properties of logarithms again. Okay, logarithms. So if you have this, 1/3 times log of base 2 of x plus log base 2 of x plus 1, the algebraic expression here. All right, if you have same bases, you can combine them. So, if you have a sum, according to the product rule for logarithms, this can be reduced to the log of base 2 of x times the quantity x plus 1. Normally when you have the product rule, it starts as a product, right? They're factors, hence the dot. And then you can break it into a sum, that they each get the same log, but you're condensing in this arrangement. This is still multiplied by 1/3, but now you've gotten it down to 1 logarithm. So now what you could invoke is the power rule. And the power rule normally is when you have an exponent, you can write it here. Well, the power rule in reverse is that you can put the exponent there. Which means that you have this, the log base 2 of the argument x times x plus 1, the whole thing to the 1/3. Remember, this is rational notation when you see a fraction, and you could convert it, if you like, into radical notation. So a radical notation, the denominator is the index. So this would be log base 2 of the cube root of x times x plus 1. The whole thing technically to the first. Like that. It's kind of overkill. The simplest way to write it would be like this. And then you could, like, that's not one of the, I didn't give you multiple choice, but if you wanted to, you could expand this, condense that. Log 2 of the cube root of x squared plus x. Either write it like that or write it like this. Okay, now that's just familiarizing a person with the properties of logarithms and incorporating also the rules for exponents. The practical or more practical application of that would be to solve equations. So let's say we started with this. Solve the exponential equation by converting to a logarithmic equation. All right, there's some procedures to this, but let me write the thing first. 32. Almost 4 hours. Okay. 3 times 2 to the x is equal to 42. It is an exponential equation because the variable is in the exponent. Now what you want to do first is you want to isolate the base. So that means move 3. If it's being multiplied, divide by 3 here, divide by 3 here, then you have 2 to the x is equal to 114. Okay. Now, what you could do is take the log of both sides, right? But what might be practical, we'll try to translate this. Let me say that first. If you can get away with it, if it is possible, try to translate into same bases, each side of equals, here and here, all right? Failing that, this is step 2, all right? If you can't do that, because then it would be 1-to-1. And you could just say that you could just compare the exponents as an equation. If you can't do that, right, and it wouldn't work in this case, you could apply a logarithm to both sides. And then you end up with something that would be, it doesn't matter which you use, right? Apply a log, same bases, to both sides, right? What would be most clever, more clever, would be to apply a log that matches the base that happens to be here. So for example, if the base of this exponent is 2, then what you could do to be clever is this. Just apply the log of base 2 to the 2, all right? And you have to do it to both sides to make it legal. All right, how come? Because if these are the same, these are inverses. All right, and then the power rule is also what's going on here. All right, the power rule would have you have the x up in the front. All right, the fact that these are inverses, properties of inverses say that this is really just 1. And then the other side is just this, log of 2 of 14. So your answer is this. You'd have to enter this into your calculator potentially, and you'll figure out what, a very precise decimal would be. Let me just show you what would happen if you just applied any old log to both sides. So in other words, an alternate reality in which you, from here, you just went with log base 10, right? There's no sin in that. But you would have to do it to both sides. And then the power rule would have you put the x here, all right? And then you would divide each side by log of 2. And you would have, this would cancel here, and you'd have x is equal to this ratio, according to the change of base formula. What you can condense this to would be the log of that base and that argument. You'd get the same answer. Now, if you did enter this into your calculator, you would have this. About, if it's not specifying any particular place, 3.807, something like that as a decimal. Now, if you're curious how to get this on your calculator, if you have newer software, all right, there's a couple of tricks you can use. You can go through the math button, and I want to say it's number. Let me see if it's not down here. No, it's the bottom of this math directory here. You see log base, and then it will let you, if you choose A, I'm going to just scroll up. It will intuitively allow you to select a base and an argument. All right. Alternatively, quit here. If you go through alpha, and then I want to say choose menu 2, you can get to it a little bit faster, perhaps. Same thing. 2 and then 14. And then you have a 3.807, whatever it is, into infinity. I'm going to just test something because I'm like, really can't help myself. If this is correct, then if I went back to the original equation, 3 times 2 to the x, and I put in what the value we arrived at for x, this should be very close to 42. The reason it's not being exact is because I rounded it. 41.9, right? That's the answer. Very good. Okay. Time to erase. Okay. 33. Oh boy, this is a long video. 33 is something that, there might be more than one way to do this, but to me, if you have something that looks like this, you might try an old technique. If you have something that is kind of trinomial-esque, meaning trinomial-like, I really can't call it a trinomial because it's not an algebraic function, it's transcendental. what you need to do is try U substitution. So if something is like 3 terms, like you see, set equal to 0, and 2, there's the same, nothing but the same type of base involved. Let's see. Well, in other cases, the same letter, same variable. And the degree of the first term is double the degree of the second term. And lastly, 4, if the third term is a constant, then this is a prime candidate for something called U substitution. Also, I should say this is in descending order, set equal to 0. U substitution is a way of not getting distracted by complicated details. Right? You're going to deal with everything eventually, but let's say that you said, well, rather than write 3 to the x, which is a nuisance, what if you just call this u? Right? That means that u represents e to the x. Right? Then this plus 2 would still be here. And this could be reinterpreted as basically u squared. Right? The reason for that being that if it's u squared, that means that it's really e to the x squared, and according to the power rule, you would simply multiply those, it would still be 2x. Anyhow, in this form, this is easy to factor, all right? Factoring helps me solve this because it's a quadratic-like problem. So if you have a quadratic trinomial-esque in descending order, I'm going to factor and then try the 0 product rule. And I eventually have to reverse substitute, but so be it. If this is a trinomial, it usually factors like this. U squared would be the same as saying a u, and a 2 is a 2 and a 1. And in this case, they both have to be minus to add to make a bigger negative, and multiply to a positive. Now at this point, I could solve each one of these little equations via the 0 product rule, which is to say that u is equal to positive 1 in this case, and u is equal to positive 2 in this case. Now I'm going to reverse the substitution. If u is standing in for e to the x, then this is e to the x is equal to 1, and e to the x is equal to 2. All right. And now I can pull tricks. All right. What I'm going to do is apply natural log to both sides. So the natural log of e to the x is equal to the natural log of 1. And in the other case, the natural log of e to the x is equal to the natural log of 2. Why natural log and not anything else? Well, you could do anything else if you want, but it would be convenient in this case because natural log is base e, which means that these are inverses. And inverses are going to amount to 1. So this would be 1. The power rule at the same time would suggest that this x would go here. So it will be x times 1, which is just x. Which means that your answer for this one is that x is equal to the natural log of 1. Whatever that decimal is. And in this instance, the exact same thing. If this is really 1, this is x to the 1. So this is x is equal to the natural log of 2. 0.693, whatever it is. Okay, if you got the decimal here, 0.693 approximately. In the case of the natural log of 1, this is equal to 0. So 0 and 0.693. Okay. 34. Solve the logarithmic equation by converting to an exponential equation. This is that technique again from before, where you cleverly apply a log of the same base as the base given. So, if this is what you have, we call that exponentiating. Exponentiating. If you're given, this is 34. If you're given the natural log, the log of base 5 of the argument 3x is equal to 4, it's an equation, this is an equal sign. There's a couple of things you can do, all right? If you were doing it in perhaps the more traditional way, it's to isolate, the log, first of all. That would mean move this 2, divide by 2. And then you would have this, the log of base 5 of 3 to the x is equal to, the outcome of this is 2. Then just, translate into, the exponential form. Which is to draw the jelly bean. This is 5 squared is equal to 3x, right? Which is 25 is equal to 3x. Divide by 3. X, although it's not a pleasant number, it's a crummy number, because it's improper, right? 25 divided by 3 is 8 in the third, right? Or you could say 8.3 repeating, right? That's what x is, right? If you try it in that other clever technique, which I do like, right? It would be at this point, right? This point of taking the log of base 5 and raising it to a base, or applying the base. Let me put this in a different color. All right. This is an alternative. Apply base 5 to both sides, which would be, you put a 5 here, you put a 5 here, right? These, according to the inverse property, are inverses. And the result is that the argument is now on the normal tier. And then you have 25 again, and you divide by 3, and you get the same answer. Okay. Problem 35, 35, is a word problem. And I really like this one because it has to do with radioactivity. It says, when an organism dies, I wrote this, the total amount of carbon-12, which is stable non-radioactive carbon, in its body remains fixed, while the total amount of carbon-14, which is naturally radioactive, just continues to decay over time without replenishment from a food source. Now, basically what happens is that it undergoes something called a beta decay, and in a beta decay, the easiest explanation of it is that it fires out a carbon-14 nucleus, will fire out an electron, but from its neutron source, right? So I know that you think of electrons as flying around a nucleus, right? Well, that's true, but a neutron, in theory, if you were to break it up into subatomic particles, one of them would be an electron, all right? And that's called a beta decay. All right. Anyhow, what results is that you end up with a positive particle left behind. All right. And that means that it changes from being carbon into the next higher element, which would be nitrogen 14. Anyhow, I put this little joke here, right? When an organism dies, the total amount of carbon-12 remains fixed, while the total amount of carbon-14 continues to decay over time without replenishment from a food source, because dead people don't eat. And that's true. All right. Normally, i.e. when we're alive, the ratio of carbon-14 to carbon-12 is 1 in a trillion. All right. To estimate the age of a fossil, the number of years since the organism died, scientists use a formula based upon exponential decay. Now, remember what exponential decay looks like. In general, here's a graph, right? It would look like this. It has an asymptote, you know, and it goes through the point 0, 1. And if you were to backtrack a little bit, you didn't have to do this, but -1, at this coordinate, -1, you would have E, which is the number 2.71, whatever it is. Anyhow, it curves this way, downwardly, rather than up, because it's a decay. And you have this formula that is used. R is equal to 1 over 10 to the 12th, all right, times E to the negative, I hate the way this was written, but it looks like this. All right. If I wrote it out a little bit more nicely than I had because of the way I had to type it, this is what it would look like in a more intuitive way, where there's a fraction and then a fraction. All right. Anyhow, to estimate the age of a fossil, scientists use this formula and basically compare what is, right, to what should be, right? That is the ratios of carbon-12 to carbon-14, what they should be and what is going on in the fossil. All right. Anyhow, using this information, answer 35. Estimate the age of a newly discovered fossil for which the carbon-14 to carbon-12 ratio is this. 1 to 10 trillion, which is what 1 over 10 to the 13th would be. Okay. We would have to manipulate this to figure out the age of the fossil, which is time. Now, what I had suggested you do to begin with was in 2 parts here. I said compare the exponential model, which is the y equals x version of this, to the given formula to translate what the variables are standing in place of. Here's what I mean. The model, I'll put it here, just above it, or maybe just next to it, is y equals a to the e to the bx. And because it is a decay model rather than a growth, it's got a negative up in the front, right? So you can see by comparing, you know, the model for exponential decay with the formula that is used for carbon dating something, that there is symmetry here. Okay. Y is standing in place of R, which is a ratio. All right. And in this particular problem, it's 1 to 10 trillion. The A, which is just a constant that would be sitting here, is this ratio. That is the normal ratio of 1 to a trillion. Right? It's the same ratio. A is that factor. E is E in all cases. All right? Now this one is a little bit more interesting. Yes, there's a negative here, so that's the same. But which of these is actually the x? If this is under normal circumstances, a function is, y is a function of x. In this instance, this is the only variable that you see here is t. This is a function of time. In years, versus this, which is a function of x. Anyhow, that's what this is. X is t in the unique formula here. That means that this number that you see here, which is a fraction of, if I were going to sort of expand it, 1 over 8,223, that's the B factor that is part of the model, all right? That comes from half-life, all right? It's some kind of derivative of, what do they call it? It involves half-life of something, but it's also slightly more complicated than that formula. It's a decay constant, that's it. This is a decay constant that would need to be used uniquely to this problem, right? That's standing in for B, it just so happens to be this fraction, rather than a regular number. Anyhow, to answer the question, really, which is part B here, I wanted you to substitute in this value of 1 to 10 trillion, right? And then solve for t. Now, in order to solve for t, it's exponential. We're going to have to apply a natural log at some point. But you can do that maybe in different points, depending upon what your preferences are. I, sticking with sort of the system that we have established, would do it this way. Try to put procedures here. Isolate, spell it. Isolate the base as you normally would. That means move this 1 to 10 over here. So how would I do that? Well, the opposite of multiplying is to divide. So even though it's a fraction, and it's kind of cumbersome, I'm going to do that immediately. 1 over 10 trillion over, divided by 1 over a trillion. Right? They're awful numbers, but we can get away with pulling tricks. If this is a complex fraction, i.e. a fraction divided by a fraction, then it's no worse than basically keep, change, flip. Which means, and to examine the intricacies of this for a moment, that it is 1 over 10 to the 13th divided by 1 over 10 to the 12th, which is 1 over 10 to the 13th times 10 over 12, 10 to the 12th over 1, all right? And that consolidated would be 10 to the 12th over 10 to the 13th. Now, you could talk yourself through this process, right? This represents a trillion. This represents 10 trillion. So even without employing rules of exponents, which I'm going to, all right, which involves just subtracting these according to the quotient rule for exponents, you're going to get a fraction, all right, of 1/10. Because the ratio of 1 to 10 that's 1 trillion versus 10 trillion, is going to simplify it down to that, even as vast as quantities as these are. Anyhow, how would you write that intricately so? 12 minus 13, according to the quotient rule, would produce what? 10 to the negative first, all right? Which you can leave like that, or conform to the better etiquette, which is to write it like that. The bottom line is that the work here is going to result in just 1/10 on this side. That's the ratio of those two things combined. And now you still have this, e to the negative t over 8,223. Okay? And I need the space, so I have to erase this. What happens next is we're looking to solve for time, because it's asking how long does this thing take, how old is this fossil? Well, we need to figure out what t is, which is years. In order to get it down to where we need it, we're going to apply natural log because of inverses. The base e I'm just writing it on this side of equals instead, doesn't really matter. If I apply the natural log of this, I would have to be consistent to do it to both sides. The power rule is going to bring this down, and you're going to end up with T over 8,223 times, these being inverses, it's just 1. We have T exposed, you know, sort of, and in the proper sort of place. You could write this as the fraction 1/10, right? And we could make it a difference if you like that instead, natural log of 1 minus the natural log of 10. It's more concise that way, right? But do manipulate. If this is really negative T over 8,223, what I might strategically do is multiply by negative 8,223 to cancel out here, including that sign, and then just plop it on the opposite side times what was there, the natural log of 1/10. And what that leaves me with is this, to enter. Time in years is whatever 8,223 times the natural log of 1/10 is. You get something like 18,000 years, a little bit more than that. 18,934 years approximately is how old the fossil would be, right? Based upon how much carbon-14 it has. And they have to do this with things that were alive, you know, at one point. You can't do it with something that doesn't ingest it, I suppose. Okay. All right. Okay. Last problem. Okay. And I've almost 4.5 hours. Yike. All right. This was from the appendix A5, which is to solve radical equations. A radical equation, all right, looks like this. 2x plus 7, and then outside the radical is x equals 2. You want to isolate the radical. And then 2, you could do it one of two ways. You could perform the opposite operation, the most basic technique, but what that really means is that you could raise the radical to its to a fraction, that is its reciprocal. Okay, what do I mean? Well, let's isolate first. Move x by adding. Then you have this. The square root of 2x plus 7 is equal to 2 plus x. Well, I'm going to put the x in front because I like it like that. X plus 2. This is a square root. The opposite of square root is to square. That's the opposite operation. That's the perspective of cancellation effect. All right? If you instead had this in rational notation, I'm just saying hypothetically that if you had it written like this, you know, if this is a square root, it's a 2 and that's a 1 in theory. And in the style of rational notation, this is radical notation versus rational notation. Then raising this to its reciprocal, 2 over 1, right, would cause the same effect. Right? You'd have to put 2 over here anyway. Right? Anyhow, what ends up happening is that the guts here, the radicand, 2x plus 7 are now exposed to the open air. On this side, you have the perfect square trinomial, which if you have it memorized, right, would help you predict the outcome of this. If you feel more comfortable, then write it expanded and then FOIL it. It's going to be x squared plus 4x plus 4. That's the result. Now, blend together all the parts, right? Set equal to 0. So if I scoop minus 7 over here, park it under set 4, and 2x, then what's left behind is this. 0 is equal to x squared, this is positive 2x, and this is negative 3. What I could do now is attempt to factor it, and then use the 0 product rule, which gets thrown around a lot, right? What happens as a result of that is what this looks like factored is x and x equals 0. I just have a preference to put 0 here. 3 is 3 and 1, and this would be positive and that would be negative to make simultaneously a positive 2 in the middle and a negative 3 in the end. The 0 product rule would say only this chunk is 0, so x minus 1 equals 0, and this is x plus 3 equals 0. Solving for each of these, you get x is equal to positive 1, and minus 3 in this case, you get x is equal to negative 3. Now, in terms of arithmetic and algebra, that's it. But there's something that we have to be careful of. I'm losing my voice. We're going to, as an extra step, check for extraneous solutions. Extraneous solutions are algebraically correct answers that when you go back to the original equation don't work. It's not your fault, all right? It's just something that naturally arises as a result of squaring. They come from multiplying or dividing a variable, a letter, or squaring. So anytime that happens, you need to really check for extraneous solutions. It's just a matter of plugging the answers that you get, and there's 2 of them, into the original equation and see if it makes sense. If it doesn't make sense, then you just eliminate that as a possibility. So, if this is the original equation, I'll write it twice in green. 2x plus 7 minus x equals 2. And then write it again here. 2x plus 7 minus x equals 2. Then I'll insert positive 1 here, in here, and negative 3 here and here. And see if it ends up making logical sense on both sides of equals here, by comparison. This is going to be 2 plus 7, which is going to be 9, and the square root of 9 is 3. 3 minus 1 is 2. Does 2 equal 2? Yes, this is a good answer. Positive 1. This is negative 6 plus 7, which is positive 1, thank God. It's not imaginary. That would be a dead giveaway, then forget it. It's not going to work. The square root of 1 is 1. This is a double negative, which means that you have a positive 3. That means that the end result here is 4 equal to 2. No, that is not true. So therefore, this is a dud, otherwise known as an extraneous solution. The only answer is this. X equals 1. And that, folks, is all she wrote. All right? That doesn't make that, whatever. I'm over tired now. I'm sorry for the length of this video, and it's going to take a while to upload, so it'll probably be like midnight by the time it uploads. Anyhow, that is the solutions to this 36 problem MAT-143 final exam. All right? I'll take this opportunity to say goodbye to you, unfortunately, because I can't do that in person. Anyhow, if you need anything, send me an email. I hope to see you again in the future, all right? And under better circumstances, okay? Be careful out there, all right? Take care.